The ocean has always held mysteries that captivate the human imagination. We look up at the stars and dream of what lies beyond our planet. Yet right here on Earth, beneath the waves, exists a realm so alien and unexplored that it might as well be on another world. Today, we're going to journey to the deepest point on our planet's surface, a place where the pressure could crush a car like a tin can, where darkness is absolute, and where life exists in forms that challenge everything we thought we knew about biology. We're diving into the Mariana Trench, and more specifically, we're going to explore what really lies at its bottom. Before we can understand what's at the bottom of the Mariana Trench, we need to understand what this place actually is. The Mariana Trench is a crescent-shaped scar in the floor of the Pacific Ocean, stretching for approximately 1,580 miles. To put that in perspective, if you were to drive that distance, you'd be traveling roughly from New York City to Denver, Colorado. This isn't just a crack in the ocean floor. It's a massive geological feature that represents one of the most extreme environments on our entire planet. The trench is located in the western Pacific Ocean, to the east of the Mariana Islands, near Guam. If you were to look at a map, you'd find it sitting roughly between Japan and Australia, though closer to Japan. The islands themselves, which give the trench its name, are part of the United States territory, though they're thousands of miles from the continental United States. The trench follows the line of these islands, running roughly north to south, creating a boundary between two massive plates of the Earth's crust. Now, when we talk about depth, the Mariana Trench isn't just deep, it's incomprehensibly deep. The deepest point of the trench is called Challenger Deep, and it sits at approximately 36,200 feet below the surface of the ocean. Let's try to wrap our minds around that number, because it's truly staggering. If you took Mount Everest, the tallest mountain on Earth, and placed it at the bottom of Challenger Deep, the peak of Everest would still be covered by over a mile of water. More than 7,000 feet of water would sit above the mountain's summit. The pressure at the bottom of the Mariana Trench is more than 1,000 times the atmospheric pressure we experience at sea level. It's approximately 8 tons per square inch. Imagine having 8 tons, the weight of about 5 cars, pressing down on every single square inch of your body from all directions simultaneously. The discovery of the Mariana Trench is a story that spans more than a century and involves the evolution of our technology and our desire to explore the unknown. The first measurements of the trench came in 1875 during the HMS Challenger expedition. This was a British scientific expedition that travelled the world's oceans, taking measurements and collecting samples. Using weighted ropes, the crew of the Challenger measured a depth of about 26,850 feet. This was revolutionary at the time. Nobody had conceived of such depths existing in the ocean. The deepest point of the trench was later named Challenger Deep in honor of this ship and its pioneering crew. However, those early measurements, while impressive for their time, were not entirely accurate. It wasn't until the 1950s that we began to get more precise readings of the trench's true depth. In 1951, another British ship, the HMS Challenger II, returned to the area with more advanced equipment called echo sounders. These devices work by sending sound waves down to the ocean floor and measuring how long it takes for the echo to return. The speed of sound in water is known, so by measuring the time delay, you can calculate the depth. It was during this expedition that the truly staggering depth of the trench was confirmed. But measuring the depth from the surface was one thing. Actually going down there was another challenge entirely. The first humans to reach the bottom of the Mariana Trench were Jacques Piccard, a Swiss engineer and explorer, and Don Walsh, a United States Navy lieutenant. On January 23, 1960, these two men climbed into a specially designed submersible called the Trieste and began their descent into the abyss. The Trieste was an unusual craft. It was a bathyscaphe, which is essentially a free-diving submersible. It used gasoline, which is lighter than water, to provide buoyancy, and iron pellets for ballast. To descend, the craft would hold onto the iron pellets. To ascend, it would release them. The descent took nearly 5 hours. Imagine sitting in a cramped sphere barely 6 feet across, surrounded by walls of steel, as you sink deeper and deeper into darkness. The temperature inside the sphere dropped as they descended. The men could hear the metal hull creaking and groaning under the increasing pressure. At about 30,000 feet, they heard a loud crack. A piece of the outer window had fractured, but the main viewing port held. They decided to continue. Finally, after 4 hours and 48 minutes, they touched down on the bottom of Challenger Deep. They had reached a place where no human had ever been before, a place more remote than the surface of the moon would be 9 years later when Neil Armstrong took his famous first steps. What they saw through their small viewing port was remarkable, if somewhat limited by the sediment their landing had disturbed. But they did see something crucial, something that would change our understanding of life on Earth. They saw a flatfish, a creature that looked similar to a flounder or a sole, swimming along the bottom. They also saw what appeared to be shrimp. In that moment, a fundamental assumption about the limits of life was shattered. Scientists had theorized that the extreme pressure at such depths would make life impossible beyond a certain point. But here was life, complex life, thriving in the deepest place on Earth. The Trieste dive was an incredible achievement, but it would be more than 50 years before humans returned to the bottom of the Mariana Trench. In 2012, filmmaker and explorer James Cameron, known for directing movies like Titanic and Avatar, became the third person to reach Challenger Deep and the first to make the journey solo. He descended in a specially designed submersible called the Deep Sea Challenger, which he had helped develop over many years. Cameron's dive lasted several hours, and he was able to collect samples and capture high-definition footage of this alien world. His expedition brought renewed attention to the deep ocean and sparked new interest in exploring these extreme environments. Since Cameron's dive, there have been additional expeditions to the Mariana Trench, including a dive by Victor Vescovo in 2019 in the submersible limiting factor. Vescovo actually made multiple dives to the bottom, and his team's surveys suggested that Challenger Deep might be even deeper than previously thought, possibly reaching 36,070 feet at its deepest point. With each expedition, we learn more about this extraordinary place, but many mysteries remain. So what exactly is down there? What's really at the bottom of the Mariana Trench? Let's start with the physical environment. The bottom of the trench is not a flat, sandy expanse like you might find on a beach. In many areas, it's a soft, muddy sediment called ooze. This ooze is made up of the remains of tiny organisms that have died in the upper layers of the ocean and slowly drifted down over thousands or even millions of years. This constant rain of organic material, called marine snow, is one of the few sources of nutrients in the deep ocean. The sediment can be several feet thick in places, and when submersibles land on it, they often create clouds of disturbed particles that can take hours to settle. The temperature at the bottom is just above freezing, hovering around 1 to 4 degrees Celsius, which is about 34 to 39 degrees Fahrenheit. It's cold, but not as cold as you might expect. The extreme pressure actually prevents the water from freezing at normal freezing temperatures. The environment is also completely dark. No sunlight penetrates to these depths. Any light that exists comes from bioluminescent organisms, creatures that can produce their own light through chemical reactions in their bodies. But despite these extreme conditions, life is there. And not just microbial life, though there's plenty of that, but complex multicellular organisms that have adapted to thrive in this harsh environment. Let's talk about some of the creatures that call the Mariana Trench home. One of the most famous residents of the deep ocean is the amphipod. These are crustaceans, relatives of the shrimp and crabs you might be familiar with. But the amphipods found in the Mariana Trench are special. They're enormous by amphipod standards, some reaching lengths of over 12 inches. For comparison, most amphipods you'd find in shallow water are less than an inch long. These giants have been found at depths exceeding 33,000 feet. What makes these amphipods so remarkable is how they survive the pressure. Their bodies contain special molecules called piezolites, which help stabilize their cellular structures under extreme pressure. Essentially, these molecules prevent their cells from being crushed. The amphipods at the bottom of the Mariana Trench also have a different diet than their shallow water cousins. They're scavengers, feeding on whatever organic material drifts down from above. including the carcasses of larger animals like fish and whales that sink to the bottom. Speaking of larger animals, there are fish in the Mariana Trench, though they become increasingly rare as you go deeper. The deepest fish ever recorded was a snailfish, observed at a depth of 27,000 feet in the Mariana Trench. Snailfish are remarkable creatures. They're small, translucent, and somewhat tadpole-like in appearance. They have no scales, and their bones are not fully mineralized, which helps them withstand the pressure. Their bodies are mostly made of a gelatinous material that's incompressible. Some species of snailfish found in the trench have been found to have high levels of a compound called trimethylamine N oxide, or TMAO, in their cells. This compound helps protect their proteins from being denatured by the extreme pressure. Below the depth where fish can survive, around 27,000 feet, you enter what's called the Hadal zone. The word Hadal comes from Hades, the Greek underworld, and it's an apt name. This is the deepest part of the ocean, and it's largely the domain of invertebrates, creatures without backbones. Here you'll find sea cucumbers, slowly crawling along the bottom, filtering organic material from the sediment. There are also various types of worms, including polychaete worms, which burrow through the mud in search of food. One of the most surprising discoveries in the Mariana Trench has been the presence of single-celled organisms called xenophyophores. These are some of the largest single-celled organisms known, with some individuals growing up to 4 inches in diameter. That's enormous for a single cell. They live on the ocean floor and feed on organic particles. What makes them particularly interesting is that despite being single-celled, they're quite complex, with multiple nuclei and intricate internal structures. Scientists believe these organisms might play an important role in the deep ocean ecosystem by processing sediment and making nutrients available to other organisms. Microorganisms, including bacteria and archaea, are abundant at the bottom of the Mariana Trench. Some of these microbes are unlike anything found elsewhere on Earth. They've evolved unique metabolic pathways that allow them to extract energy from chemical reactions rather than from sunlight or from consuming other organisms. For example, some bacteria in the trench can break down hydrocarbons, including oil and methane, using them as an energy source. This is particularly interesting because there are natural hydrocarbon seeps in some areas of the trench where these chemicals bubble up from beneath the ocean floor. But not everything at the bottom of the Mariana Trench is natural. One of the most disheartening discoveries from recent expeditions has been the presence of human-made pollution. In 2018, a study found that amphipods collected from the Mariana Trench contained high levels of persistent organic pollutants, including polychlorinated biphenyls, or PCBs, and polybrominated diphenyl ethers, or PBDEs. These are industrial chemicals that were banned decades ago, but persist in the environment. The levels found in these deep-sea creatures were similar to, or even higher, than those found in some of the most polluted rivers in China. This was a shocking discovery. It showed that human pollution has reached even the most remote place on Earth, a place that no human visited until 60 years ago. Plastic has also been found in the Mariana Trench. During his dive, Victor Vescovo reported seeing what appeared to be a plastic bag and candy wrappers at the bottom of Challenger Deep. Other expeditions have found microplastics, tiny fragments of plastic less than 5 millimeters in size, in sediment samples from the trench. These findings are a sobering reminder of the reach of human activity and the impact we're having on even the most isolated ecosystems on our planet. The geology of the Mariana Trench is as fascinating as its biology. The trench exists because of a process called subduction. The Earth's crust is divided into large plates that are constantly moving, albeit very slowly. The Mariana Trench marks the boundary where the Pacific Plate is being pushed beneath the smaller Mariana Plate. As the Pacific Plate descends into the Earth's mantle, it creates this deep trench. This is an active geological process, and the area around the trench is seismically active, meaning earthquakes are relatively common. One of the interesting features of subduction zones is the presence of hydrothermal vents. These are places where heated water from beneath the ocean floor is released back into the ocean. The water can reach temperatures of several hundred degrees Celsius. Around these vents, unique ecosystems develop, based not on photosynthesis, but on chemosynthesis. Bacteria use chemicals in the hot water, particularly hydrogen sulfide, as an energy source, and these bacteria form the base of a food web that includes tube worms, clams, and other specialized creatures. While most of the famous hydrothermal vents are found at mid-ocean ridges, some exist in subduction zones, like the Mariana Trench, adding another layer of biological diversity to this already remarkable environment. The Mariana Trench also contains mud volcanoes. These are not like the volcanoes you might imagine, with lava and dramatic eruptions. Instead, they're mounds on the ocean floor where liquid mud, gases, and sometimes solid fragments are erupted from deep beneath the surface. These mud volcanoes can create unique chemical environments that support specialized microbial communities. Some scientists believe that studying these environments could provide insights into how life might exist on other planets or moons in our solar system, particularly those with subsurface oceans like Europa, one of Jupiter's moons. The exploration of the Mariana Trench is also helping us understand the limits of life on Earth. By studying the organisms that live in these extreme conditions, scientists are learning about the biochemical and physiological adaptations that make life possible under such intense pressure. This research has implications beyond just understanding the deep ocean. It's relevant to astrobiology, the study of potential life beyond Earth. If life can thrive at the bottom of the Mariana Trench, under crushing pressure, in complete darkness, and near freezing temperatures, then perhaps life could exist in similarly extreme environments elsewhere in the universe. The technological challenges of exploring the Mariana Trench cannot be overstated. Building a submersible that can withstand the pressure at these depths is incredibly difficult. The pressure is so extreme that even tiny flaws in materials or construction can be catastrophic. The sphere that holds the human occupants must be perfectly spherical, because any imperfection creates stress concentration points where failure could occur. The materials used must be extraordinarily strong, yet light enough to allow the submersible to be maneuverable. Titanium and specialized ceramic materials are often used, but even these must be carefully tested and certified. Communication is another challenge. Radio waves don't travel well through water, so submersibles can't use traditional radio communication once they're submerged. Instead, they use acoustic communication, sending messages through sound waves. However, this is much slower than radio communication, and the bandwidth is limited, making it difficult to send large amounts of data or high-resolution images in real time. Most high-definition footage and data is stored on the submersible and retrieved only when it returns to the surface. Navigation is also tricky. GPS doesn't work underwater, so submersibles must use inertial navigation systems and acoustic positioning to know where they are. Mapping the ocean floor at these depths requires specialized sonar equipment and is a time-consuming process. Even after all the expeditions to the Mariana Trench, we've only mapped a small fraction of its floor in high resolution. There are undoubtedly features and potentially entire ecosystems that we haven't discovered yet. The bottom of the Mariana Trench represents one of the final frontiers of exploration on our planet. It's a place that teaches us about the resilience of life, the power of geological forces, and unfortunately, the reach of human impact. Every expedition brings new discoveries, new species, and new questions. As technology improves and becomes more affordable, we can expect more missions to the trench and other deep ocean environments. Each dive gives us a better understanding of our planet and reminds us that even in the most unlikely places, life finds a way. The Mariana Trench stands as the deepest place in all of Earth's oceans, but to truly understand just how deep it is, we need to put it into perspective. Numbers alone don't always convey the reality of what we're talking about. When we say the Mariana Trench reaches depths of nearly 36,000 feet, that's just a number. To really grasp the enormity of this depth, we need comparisons. We need to place it alongside things we can visualize, and we need to understand how it dwarfs almost everything else on our planet. Let's start with the basics. The average depth of the world's oceans is approximately 12,100 feet. or about 2.3 miles. That's already incredibly deep. If you were standing at the bottom of an average part of the ocean, you'd have more than 2 miles of water above your head. The pressure at that depth would be enough to kill an unprotected human almost instantly. But the Mariana Trench, specifically Challenger Deep, goes down to approximately 36,200 feet. That's nearly 7 miles down. It's 3 times deeper than the average ocean depth. Think about that for a moment. If the ocean were a 3-story building, the Mariana Trench would be a 9-story building sunk into the ground where that 3-story building stands. To put this in terms of distance, we might be more familiar with, imagine driving in a car. 7 miles is roughly the distance you might drive to get to a grocery store in a suburban area, or perhaps the distance of a short commute. Now imagine that entire distance, but instead of going horizontally across land, you're going straight down into the ocean. You're descending through complete darkness, through increasing pressure, through dropping temperatures, continuously for 7 miles. It would take hours to make that journey, even in a specialized submersible designed for the task. Now let's bring Mount Everest into the picture, because this is one of the most powerful comparisons we can make. Mount Everest, located in the Himalayas on the border between Nepal and China, is the tallest mountain on Earth when measured from sea level. Its peak reaches 29,032 feet above sea level. Climbing Mount Everest is considered one of the greatest challenges in mountaineering. The air at the summit is so thin that climbers need supplemental oxygen to survive. The temperature can drop to -40 degrees Fahrenheit or colder. Hundreds of people have died attempting to reach its summit. It represents the ultimate test of human endurance in high-altitude environments. But here's the remarkable thing. If you could somehow lift Mount Everest from where it sits and place it at the bottom of Challenger Deep, the deepest point of the Mariana Trench, the mountain's peak would still be covered by more than 7,000 feet of water. That's more than a mile of ocean sitting on top of the world's tallest mountain. Let that sink in for a moment. The deepest point in the ocean is so deep that it could swallow the tallest mountain on Earth and still have room for another significant mountain on top of it. In fact, you could stack a mountain the size of Mount Washington in New Hampshire, which is about 6,200 feet tall, on top of Mount Everest, and the combined height still wouldn't break the surface of the ocean if they were sitting at the bottom of the Mariana Trench. This comparison becomes even more striking when you consider the challenges of each environment. Climbing Mount Everest means dealing with extreme cold, low oxygen, high winds, and the physical exhaustion of climbing for days or weeks. Descending to the bottom of the Mariana Trench means dealing with extreme cold, complete darkness, and pressure that would instantly crush a human body. At the summit of Everest, the atmospheric pressure is about 1/3 of what it is at sea level, which is why climbers struggle to breathe. At the bottom of the Mariana Trench, the pressure is more than 1,000 times what it is at sea level. Every square inch of surface area experiences more than 16,000 pounds of pressure. That's approximately 8 tons per square inch, or the equivalent of having 50 jumbo jets stacked on top of a person. Let's compare the Mariana Trench to other deep places in the ocean to get a sense of how it stands apart. The Atlantic Ocean's deepest point is the Puerto Rico Trench, which reaches a maximum depth of about 28,232 feet. That's incredibly deep. Deeper than Mount Everest is tall, but it's still nearly 8,000 feet shallower than the Mariana Trench. The Indian Ocean's deepest point is the Java Trench, also called the Sunda Trench, which reaches approximately 25,344 feet at its deepest. Again, this is an extraordinary depth, but the Mariana Trench is nearly 11,000 feet deeper, or more than 2 miles deeper. Even among Pacific Ocean trenches, the Mariana Trench stands alone. The Tonga Trench, located in the South Pacific, reaches depths of approximately 35,430 feet. It's close, remarkably close to the Mariana Trench's depth, but Challenger Deep still holds the record by several hundred feet. The Philippine Trench reaches about 34,600 feet. The Kermadec Trench reaches about 32,963 feet. All of these are astoundingly deep, places where the pressure and darkness create environments as alien as anything we might find on another planet. But the Mariana Trench is the deepest of them all. To understand the depth in another way, let's think about light. Sunlight can only penetrate ocean water to a certain depth. In the clearest ocean water, under perfect conditions, some sunlight can reach down to about 3,300 feet. This is called the euphotic zone, or the sunlight zone, where there's enough light for photosynthesis to occur. Below that, you enter the twilight zone, where some faint light still penetrates, but it's too dim for photosynthesis. This twilight zone extends down to about 3,300 feet to around 13,000 feet. Below 13,000 feet, you're in the midnight zone, where no sunlight penetrates at all. Ever. The Mariana Trench extends from about 18,000 feet at its shallowest edges down to 36,200 feet at Challenger Deep. This means that even at its shallowest point, the trench is in complete darkness. At its deepest point, Challenger Deep is nearly 23,000 feet below, where the last traces of sunlight fade away. That's more than 4 miles of additional depth into absolute, perpetual darkness. Let's try some other comparisons to help visualize this depth. The Burj Khalifa in Dubai is the tallest building in the world. It stands at 2,722 feet tall. It's an enormous structure that dominates the Dubai skyline. You would need to stack more than 13 Burj Khalifas on top of each other to equal the depth of the Mariana Trench. Imagine 13 of the world's tallest buildings stacked end to end, disappearing into the ocean depths, and you're beginning to approach the scale we're talking about. Commercial airliners typically cruise at altitudes between 30,000 and 40,000 feet. The Mariana Trench at its deepest point is about as deep as a commercial airplane flies high. If you could flip the ocean upside down and fly into the inverted Mariana Trench, you'd be flying at typical cruising altitude by the time you reach the bottom. At that altitude, passengers in an airplane need a pressurized cabin to survive. At the equivalent depth in the ocean, the pressure is so immense that only the most specialized equipment can withstand it. The Grand Canyon, one of the most spectacular geological features in North America, reaches a maximum depth of about 6,000 feet from rim to river. It's a breathtaking sight that draws millions of visitors each year. People stand at the edge and marvel at how deep it is, how the Colorado River has carved through layers of rock over millions of years. But you could stack 6 Grand Canyons on top of each other and still not equal the depth of the Mariana Trench. 6 of one of Earth's most impressive canyons, stacked vertically, and you're still not at the bottom of the ocean's deepest point. Let's think about this in terms of time. If you dropped a steel ball from the surface of the ocean above Challenger Deep, it would take over an hour to reach the bottom. A steel ball, which is quite dense and would sink quickly, would still take more than 60 minutes to make the journey through all that water. If you were in a submersible descending at a reasonable rate of about 500 feet per minute, which is actually quite fast for a deep-sea submersible, it would take you over an hour just to descend, and another hour to come back up. That's more than 2 hours of travel time, just to go down and come back, not counting any time spent actually exploring at the bottom. The pressure difference is another way to understand the extreme nature of this depth. At sea level, atmospheric pressure is 14.7 pounds per square inch. We're so used to this pressure that we don't even notice it. At the bottom of the Mariana Trench, the pressure is approximately 16,000 pounds per square inch. That's more than 1,000 times the pressure we experience every day. To put that in perspective, imagine the pressure of the atmosphere we breathe, then multiply it by 1,000. That's what every square inch of surface area experiences at the bottom of the trench. A human body, which contains air spaces in the lungs, sinuses, and ears, would be crushed instantly at that depth without protection. The air in your lungs would compress to the size of a grape. Your chest cavity would collapse. Death would be instantaneous. This is why exploring the Mariana Trench is in many ways more challenging than exploring space. When astronauts go into space, they're dealing with a pressure differential in the opposite direction. Inside their spacecraft or spacesuits, they maintain Earth normal pressure, about 14.7 pounds per square inch. Outside, In the vacuum of space, the pressure is essentially zero. The difference is only 14.7 pounds per square inch. Their suits and spacecraft need to contain pressure, pushing outward against the vacuum. At the bottom of the Mariana Trench, the pressure differential is more than 1,000 times greater. A submersible has to withstand 16,000 pounds per square inch pushing inward from all directions. The walls of the pressure sphere where humans sit must be incredibly thick and strong. Even a tiny flaw or crack could be catastrophic, as the immense pressure would exploit any weakness and cause the sphere to implode in milliseconds. Let's consider some other deep places on Earth for comparison. The deepest mine in the world is the Mponeng Gold Mine in South Africa, which reaches depths of about 12,800 feet below the surface. Miners working at these depths face extreme heat and pressure, and the mine requires extensive cooling and ventilation systems. Yet the Mariana Trench is nearly 3 times deeper than even this extreme man-made depth. The deepest hole ever drilled into the Earth is the Kola Superdeep borehole in Russia, which reached a depth of about 40,000 feet. This took decades to drill and required specialized equipment. The Mariana Trench at 36,000 feet is nearly as deep as this borehole, but the borehole is a narrow hole drilled into solid rock, while the trench is a vast, water-filled canyon. When we think about the deepest parts of caves, even these pale in comparison. The deepest known cave in the world is Veryovkina Cave in Georgia, which reaches a depth of about 7,257 feet. Cave divers and explorers have spent years mapping this cave system, rappelling and climbing through narrow passages. It's considered one of the most challenging caves to explore on Earth, yet the Mariana Trench is 5 times deeper than this deepest cave. 5 times. If you could somehow drain all the water from the Mariana Trench and explore it like a cave, you'd be descending for days, through passageways and chambers on a scale that's almost impossible to comprehend. The deepest swimming pool in the world, Deep Dive Dubai, reaches a depth of about 196 feet. It's designed for recreational diving and film production, and even at this relatively shallow depth, divers need to be careful about decompression sickness and nitrogen narcosis. The Mariana Trench is more than 180 times deeper than this pool. Recreational scuba divers are typically certified to dive to depths of about 130 feet. Technical divers, with specialized training and equipment, might reach depths of 300 to 400 feet. Even the deepest recorded scuba dive, made with specialized gas mixtures and years of training, reached about 1,090 feet. The Mariana Trench is more than 30 times deeper than this extreme record. To bring this back to a more everyday scale, imagine a typical Olympic swimming pool. These are usually about 6.5 feet deep. You would need to stack over 5,500 Olympic pools on top of each other to equal the depth of the Mariana Trench. 5,500 pools. If you stacked them one on top of the other, the tower would be visible from space, reaching up nearly 7 miles into the sky if built on land. The sheer volume of water above the bottom of the Mariana Trench is staggering. Every cubic foot of seawater weighs about 64 pounds. At the bottom of Challenger Deep, you have 7 miles of water above you. The weight of all that water is what creates the enormous pressure. It's estimated that the total weight of water pressing down on every square inch at the bottom of the trench is equivalent to having about 50 aircraft carriers stacked on top of a single postage stamp. Here's another way to think about the scale. If you were at the bottom of the Mariana Trench and looked up, even if the water were perfectly clear and you had a powerful light, you couldn't see the surface. The distance is too great. Light scatters and is absorbed by water. It would be like standing on the ground and trying to see an airplane flying at cruising altitude. Except the water makes it even harder because water absorbs and scatters light much more than air does. You would be in complete darkness, surrounded by pressure, with nearly 7 miles of ocean between you and the surface world. The Mariana Trench is so deep that it affects the Earth's crust beneath it. The weight of the ocean water in the trench actually causes the oceanic crust to bow down slightly. The trench represents a place where one tectonic plate is being forced beneath another, and the depression created is so profound that it's visible as a massive feature, even on global maps of the ocean floor. When we compare the Mariana Trench to Mount Everest, we're comparing two extremes of Earth's topography. If you were to measure from the summit of Mount Everest to the bottom of Challenger Deep, you'd have a vertical distance of over 65,000 feet. That's more than 12 miles of elevation change, from the highest point on land to the lowest point in the ocean. This represents the maximum relief on Earth's surface, the greatest difference in elevation you can find on our planet. It's a testament to the dynamic nature of our planet, to the forces of plate tectonics that create both towering mountains and plunging ocean trenches. The Mariana Trench is deeper than any mountain is tall. It's deeper than most of the ocean by a factor of 3. It's so deep that if you removed all the water, the trench would be a canyon that would make the Grand Canyon look like a small ditch. It's so deep that the pressure at the bottom is more than 1,000 times what we experience at the surface. It's so deep that it takes specialized equipment years to design and build just to visit it for a few hours. And yet, despite this extreme depth, despite the crushing pressure and the eternal darkness, life has found a way to survive and even thrive there. That's perhaps the most remarkable thing of all. The Mariana Trench isn't just the deepest place on Earth. It's a testament to the limits of life and the power of adaptation. A reminder that even in the most extreme environments imaginable, Earth is a living planet. The environmental conditions at the bottom of the Mariana Trench are so extreme that they challenge our very understanding of where and how life can exist. When we talk about the deepest point of the ocean, we're not just talking about a place that's far away or hard to reach. We're talking about an environment so fundamentally different from the surface world that it might as well exist on another planet. The pressure and temperature at the bottom of Challenger Deep create conditions that would instantly kill any surface-dwelling creature, including humans. And yet these same conditions have given rise to unique forms of life that cannot survive anywhere else. Let's explore exactly what these conditions are and what they mean for anything trying to exist in this extreme environment. First, let's talk about pressure, because this is perhaps the most defining characteristic of the deep ocean. Pressure increases with depth in a very predictable way. For every 33 feet you descend in the ocean, the pressure increases by approximately 14.7 pounds per square inch. That's equivalent to 1 atmosphere of pressure, which is what we experience at sea level. So at 33 feet deep, you're experiencing 2 atmospheres of pressure, one from the air above the ocean, and one from the 33 feet of water above you. At 66 feet, you're at 3 atmospheres. At 99 feet, you're at 4 atmospheres. This continues all the way down. Now let's do the math for Challenger Deep. At approximately 36,200 feet deep, we're talking about just over 1,100 times the atmospheric pressure at sea level. The exact figure is approximately 1,086 atmospheres, or about 15,950 pounds per square inch. Some sources cite it as high as 16,000 pounds per square inch, depending on the precise depth and measurement method used. Let's stick with approximately 16,000 pounds per square inch, or 8 tons per square inch, to keep our numbers simple. What does 8 tons per square inch actually mean? Imagine taking 8 compact cars, each weighing about 1 ton or 2,000 pounds, and stacking them all on top of a single postage stamp. That's the amount of pressure pressing on every square inch of surface area at the bottom of the Mariana Trench. Now extend that across your entire body. A typical adult human body has a surface area of approximately 2,000 to 2,500 square inches. At the bottom of the Mariana Trench, that means your body would be experiencing roughly 32 million to 40 million pounds of pressure across its entire surface. That's the weight of about 16,000 to 20,000 cars pressing on you from all directions simultaneously. The human body, like most life on Earth's surface, contains air spaces. We have air in our lungs, in our sinuses, in our middle ears, and in our digestive tract. Air is compressible, meaning it decreases in volume when pressure is applied. At the bottom of the Mariana Trench, the air in your lungs would compress to roughly 1/1000th of its original volume. Your lungs, which when fully inflated might hold 6 liters of air, would be compressed to about 6 milliliters. That's about 1 teaspoon. Your chest cavity would collapse inward as the air compressed. Your ribs would snap. Your internal organs would be crushed. The air spaces in your sinuses and ears would collapse. All of this would happen in a fraction of a second. Death would be instantaneous, and there would be nothing recognizable left of a human body. This is why submarines and submersibles designed to reach these depths must be built so carefully. The pressure sphere where humans sit must be thick enough and strong enough to resist this immense pressure. The submersible that James Cameron used to reach Challenger Deep in 2012, the Deep Sea Challenger, had a pilot sphere made of steel that was 2.5 inches thick. Even with walls that thick, the sphere actually compressed slightly under the pressure, shrinking by a small but measurable amount at maximum depth. The limiting factor, used by Victor Vescovo in 2019, uses a titanium sphere that's 3.5 inches thick. These spheres are designed with no weak points, no corners or edges where stress can concentrate. They're perfect spheres because that's the shape that distributes pressure most evenly. But what about the creatures that live at these depths? How do they survive when the pressure would instantly kill a human? The answer lies in their biology. Unlike humans and other air-breathing animals, deep-sea creatures don't have air spaces in their bodies. Their bodies are filled with incompressible fluids and tissues. Water doesn't compress significantly under pressure, and neither do the cells and tissues of these animals. The pressure outside their bodies is balanced by the pressure inside their bodies. They're in equilibrium with their environment. For them, the immense pressure is normal. It's all they've ever known. In fact, many deep-sea creatures would die if brought to the surface too quickly. The sudden decrease in pressure would cause dissolved gases in their tissues to come out of solution, forming bubbles, similar to what happens to human divers who ascend too quickly and get decompression sickness, also known as the bends. The cells of deep-sea creatures can also rupture when the external pressure is removed, because their internal pressure is no longer balanced by external pressure. Some deep-sea fish that are brought to the surface in nets literally explode or turn inside out because of this pressure differential. The creatures of the Mariana Trench have also evolved special biochemical adaptations to deal with the pressure. Remember those piezolites we mentioned earlier? These are organic molecules that help stabilize proteins and cell membranes under high pressure. One of the most important piezolites is trimethylamine N-oxide, or TMAO. This compound counteracts the effects of pressure on proteins, preventing them from unfolding or losing their shape. Scientists have found that fish and other organisms from deeper waters have higher concentrations of TMAO in their tissues. It's a direct correlation. The deeper the creature lives, the more TMAO it has. This compound is so effective that researchers are studying it for potential applications in protein stabilization for medical and industrial purposes. Now let's talk about temperature. The temperature at the bottom of the Mariana Trench is cold, but perhaps not as cold as you might expect, given that it's nearly 7 miles below the surface. The temperature at Challenger Deep is approximately 1 to 4 degrees Celsius, which translates to about 34 to 39 degrees Fahrenheit. It hovers just above the freezing point of water. You might wonder why the water doesn't freeze at these temperatures. The answer is pressure. The immense pressure at these depths actually lowers the freezing point of water slightly, preventing it from turning to ice, even at these cold temperatures. The water is cold because it's far from the sun's warming rays. Remember, no sunlight penetrates to these depths. The water at the bottom of the trench is part of the deep ocean circulation system. Cold, dense water from polar regions sinks and flows along the ocean bottom toward the equator, creating deep ocean currents. This water originates in places like the North Atlantic and the Antarctic, where surface water is cooled by frigid air temperatures. When this water cools, it becomes denser and sinks, eventually making its way to the deepest parts of the ocean. The journey can take hundreds or even thousands of years. The water at the bottom of the Mariana Trench might have been at the surface during the medieval period or earlier. The cold temperature at these depths creates another challenge for life. Chemical reactions, including the metabolic reactions that sustain life, generally proceed more slowly at lower temperatures. This means that deep-sea creatures often have slower metabolisms than their shallow water counterparts. They move slowly, grow slowly, and reproduce slowly. Many deep-sea fish have metabolic rates that are a fraction of what surface fish have. This is actually an adaptation to the environment. Food is scarce in the deep ocean, so having a slow metabolism means you need less energy to survive. However, there are exceptions to this cold rule. In some areas of the Mariana Trench, there are hydrothermal vents where superheated water emerges from cracks in the ocean floor. These vents can release water at temperatures of 200 to 400 degrees Celsius, which is 392 to 752 degrees Fahrenheit. You might think water can't be liquid at these temperatures, and you'd be right under normal conditions. Water boils at 100 degrees Celsius, or 212 degrees Fahrenheit, at sea level. But remember, we're talking about the deep ocean, where the pressure is over 1,000 times atmospheric pressure. This immense pressure raises the boiling point of water dramatically. At the bottom of the Mariana Trench, water can remain liquid at temperatures well above what would cause it to boil at the surface. These hydrothermal vents create pockets of warmth in an otherwise frigid environment. Around these vents, unique ecosystems develop. The warm water is rich in chemicals like hydrogen sulfide, methane, and other minerals. Specialized bacteria use these chemicals as an energy source through a process called chemosynthesis, similar to how plants use sunlight for photosynthesis. These bacteria form the base of a food chain that includes tube worms, clams, mussels, and various other creatures. Some of these organisms can tolerate temperatures that would kill most other life forms. Certain species of bacteria found at hydrothermal vents can survive and reproduce at temperatures above 120 degrees Celsius or 248 degrees Fahrenheit. These are called thermophiles or hyperthermophiles, and they push the boundaries of what we consider the temperature limits for life. But outside of these vent areas, the temperature remains consistently cold. This cold, combined with the high pressure, creates what scientists call a high-pressure, low-temperature, or HPLT environment. These conditions affect everything from the chemistry of the water to the behavior of minerals and gases. For example, at these pressures and temperatures, carbon dioxide can form solid structures called CO2 hydrates or dry ice. Methane can form solid methane hydrates, sometimes called methane ice or fire ice, because it can actually burn if brought to the surface and ignited. These methane hydrates are found in sediments on the ocean floor in many parts of the deep ocean, including the Mariana Trench. They're stable at high pressure and low temperature, but they break down if the pressure decreases or the temperature rises. The combination of extreme pressure and low temperature also affects the viscosity of water. Viscosity is a measure of how thick or resistant to flow a liquid is. Under the conditions at the bottom of the Mariana Trench, water is slightly more viscous than at the surface. It's not a huge difference, but it's measurable. This increased viscosity affects how particles settle through the water and how creatures move through it. It's one more variable that deep-sea organisms have adapted to. Another important environmental factor at these depths is the complete absence of light. We've mentioned this before, but it's worth emphasizing again. At the bottom of the Mariana Trench, you are in absolute, total darkness. No photon of sunlight has ever reached these depths and never will. The only light that exists comes from bioluminescent organisms, creatures that can produce their own light through chemical reactions. Many deep-sea creatures have evolved bioluminescence, using it for various purposes, including attracting prey, finding mates, or startling predators. The anglerfish, for example, has a bioluminescent lure dangling in front of its mouth to attract smaller fish. Other creatures produce flashes of light to confuse predators or to communicate with others of their species. The darkness also means there's no photosynthesis happening at these depths. All the energy that sustains the ecosystem must come from other sources. The primary source is marine snow, the constant rain of organic particles falling from the sunlit zones above. Dead plankton, feces, molted shells, and other organic debris slowly drift down through thousands of feet of water, eventually reaching the bottom. This is a slow and inefficient process, which is why food is so scarce in the deep ocean. Some estimates suggest that only about 1 to 2% of the organic matter produced in the surface ocean eventually makes it to the abyssal and hadal zones. The rest is consumed or decomposed on the way down. Occasionally, a larger food fall occurs. When a large animal like a whale dies in the upper ocean, its body can sink to the bottom, providing a bonanza of nutrients for deep-sea scavengers. A single whale carcass can sustain a community of organisms for years or even decades. Researchers have found that whale falls, as they're called, support specialized ecosystems with unique species that are found nowhere else. Some of these species can only survive by moving from one whale fall to another, and scientists are still trying to understand how these organisms find new food sources in the vast emptiness of the deep ocean floor. The chemistry of the water at these depths is also different from surface water. The deep ocean water tends to be higher in dissolved nutrients like nitrates and phosphates because organic matter that sinks from above releases these nutrients as it decomposes. However, it's lower in dissolved oxygen because there's no photosynthesis happening, and oxygen is consumed by the decomposition process and by the respiration of deep-sea organisms. Some areas of the deep ocean have very low oxygen levels, creating what are called oxygen minimum zones. While the Mariana Trench doesn't have the lowest oxygen levels in the ocean, the oxygen concentration is still lower than at the surface. Deep-sea organisms have adapted to these lower oxygen levels with various physiological mechanisms, including more efficient oxygen-carrying proteins in their blood and lower metabolic rates that reduce oxygen demand. The pH of the water is also slightly different. The deep ocean tends to be slightly more acidic than surface water because of the dissolved carbon dioxide from decomposing organic matter. This is separate from the ocean acidification caused by human activities, though that's also affecting the deep ocean over time. The increased acidity can affect the ability of organisms to build shells or skeletons from calcium carbonate, though many deep-sea organisms have adapted to these conditions over millions of years. The salinity of the water at the bottom of the Mariana Trench is fairly standard for ocean water, around 35 parts per thousand. This means that for every 1,000 grams of water, about 35 grams are dissolved salts, primarily sodium chloride, or table salt. The high pressure does affect how these salts behave and how they interact with other dissolved substances, but the overall salinity remains relatively constant. One more environmental factor worth mentioning is the sediment itself. The bottom of much of the Mariana Trench is covered in a layer of soft sediment, often several feet thick. This sediment is composed of the accumulated remains of countless tiny organisms that have drifted down over millions of years, mixed with clay particles and occasional larger debris. This sediment, called ooze, is soft and muddy. When submersibles land on it, they often sink several inches into it, raising clouds of particles that can take hours to settle. This sediment provides habitat for burrowing organisms like worms and provides a matrix that microorganisms can inhabit and feed upon. The combination of all these factors creates an environment that is, in many ways, more hostile than outer space. Astronauts in space face the vacuum and radiation, but they maintain normal pressure inside their suits and spacecraft. They have light from the sun and can see their surroundings. At the bottom of the Mariana Trench, you're facing pressure more than 1,000 times greater than at the surface, pushing in from all directions. You're in complete darkness. The temperature is just above freezing. Food is scarce, oxygen levels are low, and yet life persists. Life has found ways to not just survive, but to thrive in these conditions. The creatures that live here have been shaped by millions of years of evolution in this extreme environment. They've developed transparent bodies to avoid being seen in the brief moments when bioluminescent light appears. They've developed enormous mouths and expandable stomachs to take advantage of rare food opportunities. They've developed pressure-resistant proteins and cell membranes. They've developed slow metabolisms to cope with food scarcity. They've developed the ability to sense chemical cues and vibrations in the water, since sight is useless in the darkness. Every aspect of their biology is an adaptation to the extreme pressure, cold temperature, darkness, and food scarcity that define life at the bottom of the world. For humans to visit this environment, we must bring our own small bubble of the surface world with us. We must create a protective sphere that maintains normal pressure inside while resisting the crushing pressure outside. We must bring our own light to pierce the darkness. We must bring our own oxygen to breathe. We must bring our own warmth. In a sense, a deep-sea submersible is like a spacecraft, protecting fragile human life in an environment where we have no business existing. And like spacecraft, these submersibles are at the absolute limits of our engineering capabilities. Every component must be perfect. Every seal must hold. Every system must function flawlessly. Because at 8 tons per square inch, there is no margin for error. A failure at these depths would be catastrophic and instantaneous. The pressure and temperature conditions at the bottom of the Mariana Trench remind us that Earth is a planet of extremes. From the summit of Mount Everest, where the air is thin and cold, to the bottom of Challenger Deep, where the pressure is crushing and the darkness is absolute. Our planet contains environments that push the boundaries of what we thought possible. And in each of these extreme environments, life has found a way to exist, demonstrating the remarkable adaptability and resilience of living things. The Mariana Trench isn't just the deepest place on Earth. It's a laboratory for understanding the limits of life and the power of evolution to solve seemingly impossible challenges. When scientists first began exploring the deep ocean, many believed that life could not exist beyond a certain depth. The pressure, the cold, the darkness, and the scarcity of food all seemed to create an environment so hostile that nothing could survive. The deeper researchers went, the fewer signs of life they expected to find. They theorized that there would be a point somewhere in the abyss where life simply ceased to exist. The discovery of life at the bottom of the Mariana Trench shattered this assumption completely. Not only does life exist in the deepest place on Earth, but it exists in remarkable diversity and abundance. The creatures that live in the Mariana Trench are some of the most extraordinary organisms on our planet, each one a testament to the power of evolution and adaptation. Let's explore the life forms that scientists have discovered in this extreme environment and understand how they've managed to survive where survival seems impossible. Let's start with one of the most abundant and well-studied groups of organisms in the Mariana Trench, the amphipods. Amphipods are crustaceans related to shrimp, crabs, and lobsters. In shallow waters, amphipods are typically small creatures, often less than an inch long, that scuttle along the seafloor or swim in the water column. But in the Mariana Trench, amphipods have evolved into giants. Some species found in the Hadal Zone, the deepest part of the ocean below 20,000 feet, can reach lengths of 12 inches or more. These are called supergiant amphipods, and they're unlike anything found in shallower waters. One of the most famous species is Hirundaleia gigas. This amphipod has been found at depths exceeding 33,000 feet in the Mariana Trench, making it one of the deepest living creatures ever discovered. Hirundaleia gigas is a scavenger, feeding on whatever organic material falls to the ocean floor. When scientists deploy baited traps in the trench, these amphipods arrive in swarms, sometimes hundreds or thousands of individuals, all competing for the food. They're voracious eaters, capable of stripping the flesh from a dead fish or other animal in a matter of hours. Their bodies are streamlined and powerful, with strong legs adapted for walking across the soft sediment and swimming short distances. The key to the amphipod's survival at these depths lies in their biochemistry. Scientists have discovered that these creatures have extremely high levels of piezolytes in their cells, particularly a compound called trimethylamine N oxide, or TMAO. As we mentioned earlier, TMAO helps stabilize proteins and cell membranes under extreme pressure. The deeper an amphipod lives, the more TMAO it contains. Researchers have found that Hadal amphipods can have TMAO concentrations that are several times higher than their shallow water relatives. This allows their cellular machinery to function normally, even when being compressed by 8 tons per square inch. But TMAO isn't the only adaptation these amphipods have developed. Their cell membranes are also different from those of shallow water organisms. Under normal pressure, cell membranes have a certain fluidity that allows molecules to pass in and out. Under extreme pressure, membranes tend to become rigid and less functional. Hadal amphipods have modified the composition of their cell membranes, incorporating different types of lipids that remain fluid even under crushing pressure. This ensures that nutrients can enter their cells and waste products can exit, maintaining the basic functions of life. Another remarkable group of creatures found in the Mariana Trench are the snailfish. Snailfish belong to the family Liparidae, and while many species live in shallow or moderate depths, some have adapted to the extreme conditions of the Hadal zone. In fact, snailfish hold the record for the deepest fish ever observed. In 2017, a team of researchers from Japan and the United Kingdom filmed a snailfish at a depth of 27,049 feet in the Mariana Trench. This species, tentatively identified as a Mariana snailfish or Pseudoliparis swirri, was swimming gracefully despite the enormous pressure. Snailfish are remarkable creatures. They don't look like typical fish. They have no scales. Their bodies are soft and somewhat gelatinous, almost translucent. They have large heads with small eyes, and their fins are delicate and flowing. They look fragile, almost ethereal, but this appearance is deceptive. These fish are perfectly adapted to their extreme environment. The gelatinous nature of their bodies is actually an adaptation to pressure. Their tissues are filled with water and specialized compounds that don't compress under pressure. Unlike fish with swim bladders, which are air-filled organs that would collapse at these depths, snailfish have no swim bladder at all. They maintain neutral buoyancy through the composition of their tissues, rather than through gas-filled chambers. The bones of Hadal snailfish are also adapted to the pressure. While shallow water fish have fully mineralized bones that are hard and rigid, snailfish have bones that are partially cartilaginous and not fully mineralized. This makes them more flexible and better able to withstand the pressure without breaking. Their skulls are not completely closed, lacking some of the bony plates that other fish have. This might seem like a weakness, but in the Hadal zone, it's an advantage. The incomplete skull allows for slight deformation under pressure without causing damage. Scientists have also discovered that snailfish, like amphipods, have high concentrations of TMAO in their tissues. In fact, snailfish from the Mariana Trench have some of the highest TMAO concentrations ever measured in any organism. This compound is so important for life at extreme depths that researchers believe it may actually set a limit on how deep fish can live. There's a theoretical maximum depth beyond which, even with maximum TMAO concentrations, proteins would still be denatured by pressure. This limit is estimated to be around 27,000 to 28,500 feet, which is remarkably close to where the deepest snailfish have been observed. Below this depth, it appears that fish simply cannot survive, and the Hadal zone becomes the domain of invertebrates exclusively. Speaking of invertebrates, sea cucumbers are another group of organisms found in the Mariana Trench. Sea cucumbers are echinoderms, related to starfish and sea urchins. They're soft-bodied creatures that crawl along the ocean floor, feeding on organic particles in the sediment. In the Mariana Trench, scientists have observed several species of sea cucumbers, some of them quite large, reaching lengths of over 12 inches. These creatures move slowly across the muddy bottom, extending tentacles around their mouths to gather sediment and extract whatever nutrients they can find. Sea cucumbers have been filmed at depths exceeding 32,000 feet in the Mariana Trench. They appear almost ghostly in the lights of submersibles and remote cameras, their translucent or pale pink bodies gliding over the dark sediment. Like other hadal organisms, sea cucumbers have no gas-filled spaces in their bodies. Their tissues are permeated with water and are essentially incompressible. They have slow metabolisms adapted to the cold temperatures and scarce food supply. Some species can survive for months without eating, living off stored energy reserves during times when food is particularly scarce. One fascinating aspect of sea cucumber biology in the deep ocean is their role in bioturbation, which is the process of mixing sediment. As they crawl across the bottom and process sediment through their digestive systems, they mix the layers of mud and ooze, aerating it slightly and redistributing nutrients. This creates microhabitats for bacteria and other microorganisms. In a sense, sea cucumbers are the gardeners of the deep ocean floor, maintaining the health of the sediment ecosystem through their feeding activities. Polychaete worms are another important group of organisms in the Mariana Trench ecosystem. Polychaetes are segmented worms, often called bristle worms, because of the tiny hair-like structures that project from their body segments. In shallow waters, polychaetes are incredibly diverse, with thousands of species adapted to various lifestyles. Some are predators, some are scavengers, and some are filter feeders. In the hadal zone, polychaetes have been found burrowing through the sediment, creating networks of tunnels as they search for food particles. Some species of polychaetes found in the trench can reach lengths of several inches and have been observed at depths exceeding 30,000 feet. They play a crucial role in breaking down organic matter and recycling nutrients. Without these worms and other detritivores, the sediment would become depleted of oxygen and nutrients, making it uninhabitable for other organisms. The polychaetes, through their burrowing and feeding activities, keep the sediment ecosystem functioning. One of the most surprising discoveries in the Mariana Trench was the presence of xenophyophores. These are single-celled organisms, protists related to amoebas, but they're some of the largest single-celled organisms known to science. Individual xenophyophores can grow to 4 inches in diameter or larger. That's enormous for a single cell. To put it in perspective, most cells in your body are measured in micrometers, thousandths of a millimeter. A xenophyophore can be over 100 millimeters across, which is roughly 100,000 times larger than a typical human cell. Xenophyophores look like delicate, lacy structures on the ocean floor. They create shells or tests from sediment particles glued together with organic material they secrete. Inside this shell is the single cell, but it's not a simple cell. Xenophyophores are multinucleate, meaning they have multiple copies of their genetic material distributed throughout the cell. This allows them to coordinate activities across their large size. They feed by extending pseudopodia, temporary projections of their cell membrane, to capture organic particles and bacteria from the surrounding sediment. These organisms have been found at depths exceeding 33,000 feet in the Mariana Trench. James Cameron collected samples of xenophyophores during his 2012 dive to Challenger Deep. Scientists believe these organisms may play an important role in the deep ocean ecosystem by processing large amounts of sediment and concentrating trace elements and nutrients. Their shells, after they die, also provide hard surfaces in an otherwise muddy environment, which other organisms can attach to or hide under. Bacteria and archaea are perhaps the most abundant and diverse life forms in the Mariana Trench, though they're too small to see without a microscope. These microorganisms are found throughout the water column and in the sediment, performing crucial roles in nutrient cycling and energy flow. Some bacteria in the trench are heterotrophs, meaning they consume organic matter for energy, just like animals do. They break down the marine snow that falls from above, releasing nutrients back into the ecosystem. Other bacteria are chemotrophs, meaning they obtain energy from chemical reactions rather than from consuming organic matter or photosynthesis. Near hydrothermal vents and cold seeps in the trench, specialized bacteria oxidize chemicals like hydrogen sulfide, methane, and iron, using the energy released to build organic molecules. These chemosynthetic bacteria form the base of unique food chains that are independent of sunlight. Larger organisms like tube worms and clams can host these bacteria in their tissues in symbiotic relationships, essentially farming the bacteria and using them as an internal food source. Scientists have discovered bacteria in the Mariana Trench that belong to groups previously unknown to science. Some of these bacteria have unusual metabolic capabilities, including the ability to break down hydrocarbons like oil and plastic. This has both positive and disturbing implications. On one hand, these bacteria might help break down pollutants that reach the trench. On the other hand, the fact that they've evolved this capability suggests that pollutants are present in sufficient quantities at these depths that evolutionary pressure has selected for organisms that can metabolize them. Archaea, which are single-celled organisms distinct from bacteria, are also abundant in the trench. Some archaea are extremophiles, thriving in conditions that would kill most other organisms. Near hydrothermal vents, there are archaea that can tolerate temperatures above 120 degrees Celsius or 248 degrees Fahrenheit. These thermophilic and hyperthermophilic archaea may represent some of the most ancient forms of life on Earth, and studying them gives us insights into how life might have originated in extreme environments billions of years ago. One group of organisms that was once thought to be abundant in the deep ocean but has rarely been observed in the Hadal zone is sponges. Sponges are simple animals that filter water through their bodies, extracting food particles and oxygen. They're found throughout the ocean at various depths, and some species can live in very deep water. However, in the deepest parts of the Mariana Trench, sponges appear to be rare or absent. This might be because the slow-moving currents at these depths don't provide enough water flow for filter feeding to be efficient. Or it might be because food particles are so scarce that filter feeding isn't a viable strategy. Jellyfish and other gelatinous organisms have been observed in the Mariana Trench, though typically not at the very deepest points. These creatures are well suited to the deep ocean because their bodies are mostly water, making them neutrally buoyant and resistant to pressure. They drift through the water column or swim with gentle pulsations, capturing small prey with their tentacles. Some species observed in the trench are bioluminescent, producing flashes or glows of light that may be used to attract prey, deter predators, or communicate with others of their species. One of the most intriguing aspects of life in the Mariana Trench is the presence of larger predators. While the very deepest parts of the trench seem to be dominated by scavengers and detritivores, there are predatory fish and invertebrates at slightly shallower depths within the trench system. The snailfish we discussed earlier are actually predators. They have relatively large mouths and feed on smaller invertebrates like amphipods and copepods. Researchers have examined the stomach contents of Hadal snailfish and found them full of crustaceans, indicating that there's enough prey in the trench to support a population of predatory fish. There are also grenadier fish, also called rat tails, which have been observed at depths of over 23,000 feet in the trench. These fish have large heads, tapering bodies that end in long, thin tails, and sensory barbels under their chins that help them detect prey in the darkness. They're scavengers and predators, feeding on whatever they can find. Grenadiers have been a focus of deep-sea fishing in some parts of the world, though the populations in the Mariana Trench are presumably safe from exploitation due to the extreme depth and difficulty of access. Crustaceans other than amphipods are also present in the trench. Isopods, which are related to the pillbugs or roly-polies you might find in your garden, have been found at Hadal depths. Some species of deep-sea isopods can grow quite large, reaching lengths of several inches. They're scavengers with powerful jaws that can crush through shells and tough tissues. Copepods, tiny crustaceans that are abundant throughout the world's oceans, are also found in the trench, though in lower densities than in surface waters. These small creatures are an important food source for larger animals like snailfish. Mollusks, the group that includes snails, clams, and octopuses, are represented in the Mariana Trench, though they become increasingly rare at the greatest depths. The extreme pressure makes it difficult for organisms to build shells from calcium carbonate, as the chemistry of shell formation is affected by pressure. However, some small snails and bivalves have been found at depths exceeding 26,000 feet. These organisms have thinner shells than their shallow water relatives, and their shells may be reinforced with organic compounds to provide flexibility. One group of animals conspicuously absent from the deepest parts of the Mariana Trench are vertebrates other than fish. No mammals, reptiles, birds, or amphibians live at these depths. This makes sense when you consider that all of these groups are air-breathing at some point in their life cycle. Marine mammals like whales and seals can dive to impressive depths, some reaching over 9,000 feet, but they must return to the surface to breathe. The pressure at the bottom of the Mariana Trench would collapse their lungs and crush their air-filled spaces long before they reach the bottom. The deepest diving mammal is the Cuvier's beaked whale, which has been recorded diving to depths of nearly 10,000 feet. But even these incredible divers are nowhere close to reaching the Hadal Zone. Scientists have also been searching for viruses in the Mariana Trench. Viruses are not technically alive as they cannot reproduce on their own, but they play crucial roles in marine ecosystems. Recent studies have found that viruses are abundant in trench sediments and water. These viruses infect bacteria and archaea, killing them and releasing their cellular contents back into the environment. This process, called the viral shunt, is an important part of nutrient cycling in the ocean. The viruses in the Mariana Trench appear to be adapted to the high-pressure environment, with some showing genetic modifications that may help them remain stable and infectious under extreme conditions. One of the ongoing questions in deep-sea biology is how organisms at the bottom of the Mariana Trench reproduce. Food is scarce, potential mates are widely scattered, and the energy demands of producing eggs or offspring are high. Scientists have found that many Hadal organisms have slow reproductive rates. Amphipods, for example, may produce fewer eggs than their shallow water relatives, but those eggs are larger and contain more yolk, giving the developing embryos a better chance of survival. Some deep-sea fish are thought to have extended lifespans, perhaps living for decades or even a century or more, which gives them more opportunities to encounter mates and reproduce over their lifetime. Many deep-sea organisms also appear to have continuous reproductive cycles, rather than seasonal ones. In shallow waters, many marine organisms time their reproduction to coincide with seasonal increases in food availability, such as spring plankton blooms. In the deep ocean, where seasons are irrelevant and food arrives sporadically, reproduction can occur year-round whenever conditions are favorable. This strategy maximizes the chances that at least some offspring will be produced when food is available. The larvae of some Hadal organisms remain in the deep ocean throughout their development, never venturing to shallower depths. This is unusual because many marine animals have planktonic larvae that drift in surface waters before settling to the bottom as adults. But in the Hadal Zone, some species have abandoned this strategy entirely. Their larvae develop directly from the egg into miniature versions of the adults, skipping the planktonic stage. This prevents them from being swept away from the trench by currents and ensures that they remain in the habitat they're adapted to. One of the most remarkable aspects of life in the Mariana Trench is not just the individual adaptations of these organisms, but the fact that they form functioning ecosystems. Despite the extreme conditions, there are food webs, predator-prey relationships, competition for resources, and symbiotic partnerships. The trench is not a barren wasteland, but a living community, albeit one that operates at a slower pace and with different rules than ecosystems we're familiar with. The discovery of these life forms has profound implications for our understanding of biology and the limits of life. If organisms can thrive at the bottom of the Mariana Trench, under 8 tons per square inch of pressure, in near-freezing temperatures, in complete darkness, with minimal food, then where else might life exist? Could there be life beneath the ice sheets of Antarctica, where conditions are similarly extreme? Could there be life in the subsurface oceans of Europa or Enceladus, moons of Jupiter and Saturn that are covered in ice but may have liquid water oceans beneath? The creatures of the Mariana Trench expand our conception of habitability and give us hope that life might be more widespread in the universe than we previously imagined. Every expedition to the Mariana Trench discovers new species. Scientists estimate that we've only catalogued a small fraction of the biodiversity in the Hadal Zone. There are likely hundreds or even thousands of species yet to be discovered, each with its own unique adaptations and evolutionary story. As technology improves and more expeditions are funded, we'll continue to expand our knowledge of this remarkable ecosystem. The creatures of the Mariana Trench are not just curiosities or oddities. They're survivors, pioneers, and masters of adaptation. They remind us that life is tenacious, creative, and far more resilient than we often give it credit for. The question of what remains undiscovered in the Mariana Trench is one that captivates scientists and explorers alike. Despite over a century of deep ocean research and several successful expeditions to the very bottom of Challenger Deep, the truth is that we've barely scratched the surface of understanding what lives in the Hadal Zone. The Mariana Trench is vast, covering over 1,500 miles in length and varying in width from about 43 miles at its widest point to just a few miles in narrower sections. The total area of the trench system is enormous, and the amount of it that has been directly observed by humans or cameras represents a fraction of a percent. To put it simply, yes, there are almost certainly unknown and undiscovered species living in the Mariana Trench, and the number of these species is likely substantial. Let's start by understanding the scope of what we've actually explored. In the entire history of deep ocean exploration, only a handful of crewed missions have reached the bottom of Challenger Deep. Jacques Piccard and Don Walsh in 1960, James Cameron in 2012, Victor Vescovo made multiple dives in 2019 and 2020. A handful of others have also made the journey in recent years as deep diving technology has improved. Each of these missions lasted just a few hours at the bottom, and the area that could be observed through the small viewports of the submersibles or documented with cameras was limited to a relatively small patch of seafloor. Imagine trying to understand all the life in the Amazon rainforest by spending a few hours looking at a few square yards of jungle floor. That's essentially what we've done with the Mariana Trench. Even with remotely operated vehicles, or ROVs, and autonomous landers that can be deployed without humans aboard, our coverage is minimal. These devices can stay at depth longer than crewed submersibles and can be equipped with cameras, sampling equipment, and sensors. Scientists have deployed numerous landers into the trench over the past few decades, and these have captured thousands of hours of footage and collected countless samples. But even with all this effort, the total area observed is tiny compared to the trench's overall size. It's like trying to understand all of human civilization by watching a few security cameras placed randomly around the world. You'll learn something certainly, but you'll miss most of what's actually happening. This sampling limitation means that every time scientists deploy equipment into the trench, there's a reasonable chance they'll discover something new. And indeed, nearly every major expedition has returned with previously unknown species. In 2014, an international team deployed camera systems in the Mariana Trench and recorded a previously unknown species of snailfish at depths around 26,000 feet. This fish was later described as a new species and named Pseudoliparis swirei in honor of the expedition's equipment specialist. In 2017, the same general area yielded footage of snailfish at even greater depths, pushing the record for the deepest fish ever observed. During Victor Vescovo's expeditions in 2019, the team collected numerous biological samples from the bottom of Challenger Deep. When these samples were analyzed back in laboratories, they contained several species of amphipods that appeared to be new to science. Some of these are still being formally described and studied. The genetic analysis of these amphipods has revealed that they're quite different from amphipods found in other trenches around the world, suggesting that each trench system may harbor its own unique species that have evolved in isolation from one another. This brings up an important point about Hadal ecology. The deep ocean trenches of the world are like islands, separated from each other by vast expanses of abyssal plain that, while still extremely deep at around 15,000 to 20,000 feet, are not as deep as the trenches themselves. For organisms that are specifically adapted to Hadal conditions, adapted to pressures above 1,000 atmospheres, the shallower abyssal plains may actually represent a barrier they cannot cross. Just as a deep-sea creature would be killed by the rapid decrease in pressure if brought to the surface, a Hadal specialist might not be able to survive at shallower depths where the pressure is lower. Their biochemistry, tuned to function at extreme pressure, might not work properly at merely very high pressure. This means that the populations of organisms in the Mariana Trench may be isolated from populations in other trenches like the Tonga Trench, the Kermadec Trench, or the Japan Trench. Over millions of years, this isolation would lead to speciation, where populations evolve independently and eventually become distinct species. Scientists call this phenomenon Hadal endemism, and it suggests that each major trench system should have its own unique fauna. If this is true, and the evidence increasingly suggests it is, then every trench that hasn't been thoroughly explored likely contains numerous species unknown to science. But it's not just new species of known organism types that scientists expect to find. There's also the possibility of discovering entirely new types of organisms, creatures that represent evolutionary lineages we haven't encountered before. The deep ocean has surprised us before with such discoveries. In 1977, when scientists first explored hydrothermal vents, they found tube worms that can grow up to 8 feet long, giant clams, and entire ecosystems based on chemosynthesis rather than photosynthesis. Nobody had predicted such ecosystems could exist. More recently, scientists discovered the Yeti crab near hydrothermal vents, a white hairy crustacean that farms bacteria on its appendages. These discoveries remind us that the deep ocean still has the capacity to surprise us with truly novel forms of life. What kinds of unknown creatures might be lurking in the Mariana Trench? Scientists have several hypotheses based on what they know about deep-sea ecology and evolution. First, there are almost certainly many more species of amphipods, copepods, and other small crustaceans that haven't been documented. Every sample collected from the trench contains a mixture of species, and detailed taxonomic work often reveals that what appeared to be one species is actually several closely related species that look similar but are genetically distinct. This cryptic diversity is common in the ocean, and it's likely that the Hadal zone has far more species of small crustaceans than we currently recognize. Second, there may be species of fish that live at or near the maximum depth that fish can survive. We've found snailfish at 27,000 feet, which is close to the theoretical limit of around 27,000 to 28,500 feet that we discussed earlier. But it's possible there are species that push right up against this limit, living at the absolute edge of what's physiologically possible for a vertebrate. These fish would be of immense scientific interest because they would represent the extreme end of fish adaptation to pressure. Third, there are likely many species of worms, both polychaetes and nematodes, that remain undiscovered. Worms are incredibly diverse in marine environments, with thousands of species adapted to different habitats and lifestyles. The Hadal zone probably contains specialized worms that feed on specific types of organic matter, that burrow to specific depths in the sediment, or that have symbiotic relationships with bacteria. Each new sample of sediment from the trench tends to contain worms that don't perfectly match any described species, suggesting a rich diversity waiting to be catalogued. Fourth, the microbial diversity of the trench is almost certainly vastly underestimated. Bacteria and archaea are notoriously difficult to study because most species cannot be cultured in laboratories. They require the exact chemical conditions and pressures of their natural environment to survive and reproduce. Scientists use genetic sequencing to identify microbes from environmental samples, but this technique only tells us about the genetic material present, not necessarily about the full diversity of living microbes. Recent studies using advanced sequencing techniques have found that Hadal sediments contain thousands of distinct genetic signatures, each potentially representing a different species or strain of microorganism. Many of these signatures don't match anything in existing databases, suggesting entirely new groups of microbes. There's also the intriguing possibility of larger predators in the trench, that have simply eluded observation so far. While the very deepest parts of the trench seem to be dominated by scavengers and detritivores, the slightly shallower regions within the trench system, from 18,000 to 25,000 feet, might harbour predatory fish or large invertebrates that are rare enough or mobile enough that they haven't been captured on camera yet. The ocean is vast, and rare species can easily avoid detection for long periods. Consider that the coelacanth, a large fish thought to have been extinct for 66 million years, was rediscovered alive in 1938. If a 5-foot-long fish can remain hidden until the 20th century, it's certainly possible that unusual creatures remain undiscovered in the Mariana Trench. Some scientists speculate about the possibility of large squid or octopus species in the deep ocean trenches. Giant squid, which can reach lengths of 40 feet or more, are known to live in deep water, though they're typically found at depths of 1,000 to 3,000 feet, not in the Hadal zone. However, there could be specialized deep-sea cephalopods that have adapted to extreme depths. Octopuses, in particular, are known for their ability to survive in diverse environments, and some species have been found at depths exceeding 23,000 feet. It's conceivable that there are Hadal octopus species that remain undiscovered, perhaps living in rocky outcrops or caves within the trench where they could hide from passing cameras. The discovery of new species in the Mariana Trench isn't just about cataloguing biodiversity for its own sake, though that's certainly valuable. Each new species provides insights into evolution, adaptation, and the limits of life. When scientists discover a new species of amphipod, they can study its genome to understand what genetic changes allowed it to survive at extreme depth. They can study its biochemistry to learn about novel proteins and compounds that might have medical or industrial applications. They can study its ecology to understand how energy flows through Hadal ecosystems. Every new species is a piece of a larger puzzle, helping us understand how life works at the most fundamental level. Current exploration efforts in the Mariana Trench and other Hadal zones are ongoing, though they're limited by funding and technology. Deep ocean exploration is expensive. Building a submersible capable of reaching full ocean depth costs tens of millions of dollars. Each expedition requires a research vessel, crew, support staff, and months of planning. These costs mean that only a handful of organizations and wealthy individuals can afford to mount expeditions to the deepest ocean. However, the situation is improving. The success of James Cameron's Deep-Sea Challenger and Victor Vescovo's Limiting Factor has demonstrated that repeated trips to full ocean depth are possible with modern technology. Vescovo's submersible, in particular, was designed for repeated dives and has now been to the bottom of all 5 of the world's deepest trenches, a feat called the 5 Deeps Expedition. There are also efforts to develop less expensive methods of exploring the Hadal zone. Autonomous landers, which are essentially frames loaded with cameras, bait, and sampling equipment that free-fall to the ocean floor and then drop weights to return to the surface, are much cheaper than crewed submersibles. A lander might cost hundreds of thousands of dollars rather than tens of millions, making it accessible to more research institutions. These landers can be deployed for hours or even days, capturing footage of whatever creatures come to investigate the bait. Several research groups, including teams from Japan, China, the United Kingdom, and the United States, regularly deploy landers into various trenches to study Hadal life. Remotely operated vehicles, or ROVs, are another tool for exploration. These are tethered robots that can be controlled from a ship on the surface. While most ROVs aren't rated for full ocean depth, there are a few that can reach the Hadal zone. The ROV Kaiko, built by Japan, reached the bottom of Challenger Deep in 1995, only the second vessel to do so after the Trieste. Unfortunately, Kaiko was lost at sea in 2003. More recently, China has developed the ROV Haidu-1, which has explored the Mariana Trench at depths exceeding 33,000 feet. These ROVs can collect samples, manipulate objects, and conduct experiments that would be difficult or impossible with free-falling landers. Autonomous underwater vehicles, or AUVs, are untethered robots that can navigate on their own using pre-programmed routes or artificial intelligence. Most AUVs are designed for shallower depths, but there's growing interest in developing Hadal-rated AUVs that could map large areas of the trench floor and collect data over extended periods. Such vehicles could revolutionize our understanding of these environments by providing systematic coverage rather than the opportunistic observations we currently rely on. Environmental DNA, or eDNA, is an emerging technique that could help scientists discover species without even seeing them. Every organism sheds DNA into its environment through skin cells, mucus, feces, and other biological materials. By filtering water samples and sequencing the DNA fragments present, scientists can identify what species are present in an area, even if they never encounter the actual organisms. This technique has been used successfully in shallow water and terrestrial environments, and researchers are now applying it to the deep ocean. Water samples collected from the Mariana Trench contain DNA from numerous organisms, and analysis of this DNA has revealed genetic signatures that don't match any known species, providing indirect evidence of undiscovered biodiversity. International collaboration is becoming increasingly important in Hadal research. The deep ocean doesn't respect national boundaries, and the challenges of exploring it are too great for any single country to tackle alone. Organizations like the International Deep Sea Biology Society bring together researchers from around the world to share data, coordinate expeditions, and establish standards for sample collection and species description. There are also efforts to create comprehensive databases of Hadal organisms, including their genetic sequences, photographs, and ecological information. These databases allow researchers to compare findings across different trenches and time periods, helping to paint a more complete picture of Hadal biodiversity. One of the exciting aspects of ongoing exploration is the improvement in imaging technology. Early expeditions to the deep ocean use grainy black and white cameras with limited resolution. Today's cameras can capture high-definition video in full color, even in the complete darkness of the Hadal zone using powerful LED lights. Some systems can now capture 4K or even 8K video, revealing details of deep-sea organisms that were previously impossible to see. This improved imaging has led to the discovery of behaviors and anatomical features that weren't visible in older footage, essentially allowing scientists to make new discoveries by re-examining creatures that were thought to be well known. There's also growing interest in long-term monitoring of Hadal environments. Most expeditions provide a snapshot of conditions at a single point in time, but ecosystems change over days, seasons, and years. Scientists would like to understand whether there are temporal patterns in Hadal communities. Do certain species appear at certain times? Do population densities fluctuate? How quickly do communities recover after a disturbance, such as when a whale carcass lands on the bottom and attracts a swarm of scavengers? To answer these questions, researchers are developing landers that can remain on the bottom for months or even years, powered by batteries or fuel cells, continuously recording data that's periodically transmitted to satellites when the lander surfaces briefly. There's also speculation about what might be found in the sediment beneath the ocean floor in the trench. The sediment can be many feet thick, and within it there may be microorganisms living in the spaces between sediment particles, surviving on chemicals that seep up from deeper layers or on organic matter buried long ago. Some scientists hypothesize that the deep biosphere, life within the Earth's crust, might extend to significant depths below the seafloor in the trench, potentially kilometers down. If this is true, the total biomass of life in and beneath the Mariana Trench could be far greater than what we see on the surface of the sediment. One of the most tantalizing questions in Hadal biology is whether there could be large, intelligent organisms living in the trench. This veers into the realm of speculation, but it's worth considering. Intelligence and large body size both require significant energy, and energy is scarce in the Hadal zone. This makes it unlikely that there are large, intelligent creatures like whales or dolphins living permanently at these depths. However, nature has surprised us before, and it would be foolish to completely rule out the possibility of discovering something truly unexpected. The ocean is the largest habitat on Earth, and the deep ocean is by far the least explored part of it. If there's anywhere on our planet where truly alien life might be hiding, it's in places like the Mariana Trench. Scientists are also interested in how climate change might be affecting the Mariana Trench and whether this could lead to changes in the species present. The deep ocean is not isolated from surface conditions. Changes in ocean temperature, currents, and chemistry at the surface can eventually affect the deep ocean through the slow mixing and circulation of water masses. Rising ocean temperatures could change the rate at which organic matter decomposes, potentially altering the amount of food that reaches the Hadal zone. Ocean acidification, caused by the ocean absorbing carbon dioxide from the atmosphere, could affect organisms that build shells or skeletons from calcium carbonate. These changes might favor some species over others, potentially leading to shifts in community composition that could result in new species moving into the trench or existing species evolving new adaptations. The discovery of pollution in the Mariana Trench, including microplastics and persistent organic pollutants, raises questions about how these contaminants might be affecting the organisms there, and whether some species are adapting to cope with them. There may be microbes evolving the ability to break down plastics or other synthetic compounds, and these would represent new species or strains that didn't exist before the Industrial Age. While this would be a fascinating example of rapid evolution, it would also be a sobering reminder of humanity's impact on even the most remote environments. Looking to the future, there are ambitious proposals for establishing permanent research stations in the deep ocean. These would be unmanned facilities, but they could host a suite of instruments and cameras, providing continuous monitoring of Hadal environments for years or decades. Some researchers envision networks of such stations across multiple trenches, creating an early warning system for changes in deep ocean ecosystems. Such infrastructure could dramatically accelerate the pace of discovery, as scientists would have access to data from the trench at all times, rather than only during occasional expeditions. There's also interest from private companies and individuals in deep ocean exploration. Tourism to the Mariana Trench is not yet a reality, but as submersible technology improves and costs decrease, it may become possible for wealthy tourists to visit the bottom of the trench, much as space tourism is beginning to become a reality. While this raises concerns about potential impacts on the fragile Hadal ecosystems, it could also provide funding for research and increase public awareness of the importance of protecting the deep ocean. The search for undiscovered species in the Mariana Trench is fundamentally a search for understanding. Every new species discovered adds to our knowledge of how evolution works, how ecosystems function, and how life adapts to extreme conditions. These discoveries have practical applications as well. Enzymes from deep-sea microbes that function under high pressure have been adapted for use in industrial processes. Proteins that resist denaturation under extreme conditions could lead to new medical treatments for diseases involving protein misfolding. Compounds produced by deep-sea organisms could yield new pharmaceuticals. The biodiversity of the Mariana Trench is not just scientifically interesting, but potentially valuable to human society in ways we're only beginning to understand. As technology continues to advance and more resources are devoted to deep ocean exploration, the pace of discovery in the Mariana Trench will likely accelerate. We're living in a golden age of Hadal research, with more expeditions, more data, and more international collaboration than ever before. Each year brings new findings, new species, and new insights into this alien world beneath the waves. The question is not whether there are undiscovered species in the Mariana Trench, but rather how many there are and how long it will take us to find them. Based on current estimates and the rate of new species discovery, scientists believe it could take decades or even centuries to fully catalogue the biodiversity of the Hadal zone. The Mariana Trench still holds many secrets, and the journey to uncover them has only just begun. The history of deep-sea exploration is a story of human curiosity, technological innovation, and the relentless desire to push beyond known boundaries. The expeditions to the Mariana Trench, particularly to its deepest point at Challenger Deep, represent some of the most extraordinary achievements in exploration history. Each mission to these depths has been a monumental undertaking, requiring years of preparation, cutting-edge technology, and immense courage. Together, These expeditions have transformed our understanding of the deep ocean, revealing a world that's far more complex, dynamic, and inhabited than anyone had imagined. Let's journey through the history of these remarkable missions and examine what they've taught us about the deepest place on Earth. The story begins long before anyone reached the bottom of the Mariana Trench. It starts with the HMS Challenger expedition of 1872 to 1876, one of the most important scientific voyages in history. This British research vessel traveled the world's oceans, taking depth soundings, collecting samples, and documenting marine life at various depths. The ship was equipped with weighted ropes that could be lowered to measure ocean depth, a laborious process that could take hours for a single measurement. In 1875, while crossing the Western Pacific Ocean, the Challenger crew took a sounding in what would later be called the Mariana Trench and measured a depth of 26,850 feet, which they called Challenger Deep. This measurement was revolutionary. Before the Challenger expedition, many scientists believed the deep ocean was essentially lifeless, a cold, dark void where nothing could survive. The expedition proved this wrong by dredging up organisms from depths of over 23,000 feet in various locations around the world. These findings sparked a fundamental shift in marine biology, establishing that life could exist at depths previously thought impossible. However, the measurements taken by the Challenger were not entirely accurate due to the limitations of the rope-based sounding method. The rope could drift with currents as it descended, giving false readings. Still, the expedition's contribution to oceanography cannot be overstated. It laid the foundation for all future deep-sea research. The next major development came in the 1950s with the advent of echo sounding technology. Instead of lowering ropes, ships could now send sound waves to the ocean floor and measure the time it took for the echo to return. This allowed for much more accurate and rapid depth measurements. In 1951, a new British vessel, HMS Challenger 2, returned to the area surveyed by its namesake and used echo sounders to measure the trench's depth more precisely. The readings showed depths exceeding 35,000 feet, confirming that this was indeed the deepest part of the world's oceans. The deepest point was named Challenger Deep in honor of both vessels. But measuring the depth from the surface was one thing. Actually, going there was an entirely different challenge. This is where one of the most remarkable stories in exploration history begins. In the late 1950s, a Swiss physicist and engineer named Auguste Piccard designed and built a deep-diving submersible called a bathyscaphe. The name comes from Greek words meaning deep ship. Piccard had previously designed high-altitude balloons and held records for the highest altitude reached by humans, so he understood the engineering principles needed to protect humans from extreme pressure differentials. He applied these principles in reverse, creating a vessel that could protect occupants from crushing external pressure rather than explosive internal pressure. The bathyscaphe, named Trieste after the Italian city where it was built, consisted of a large float filled with gasoline, which is lighter than water and doesn't compress under pressure, and a thick-walled steel sphere where the crew would sit. To descend, the craft carried iron pellet ballast. To ascend, it would release the ballast. It was a simple but effective design. The Italian Navy initially supported the project, but in 1958, the United States Navy purchased the Trieste and brought it to California. Auguste Piccard's son, Jacques Piccard, came with the vessel as a consultant and pilot. The Navy had ambitious plans for the Trieste. They wanted to prove that humans could reach the deepest point on Earth, partly for scientific reasons and partly for military prestige during the Cold War era. Lieutenant Don Walsh, a young Navy officer and submarine commander, was assigned to work with Jacques Piccard on the project. Together, they spent months preparing the Trieste for what would be the deepest dive in history. The pressure sphere was carefully inspected for any flaws. The gasoline floats were tested. Every system was checked and rechecked. Any failure at depth would be instantly fatal. On January 23, 1960, Piccard and Walsh climbed into the cramped sphere of the Trieste, barely 6 feet in diameter and began their descent into Challenger Deep. The sphere had one small viewing port, a thick cone of acrylic that could withstand the pressure. As they descended, the temperature inside the sphere dropped. They could hear the metal hull creaking and groaning under the increasing pressure. Communication with the surface ship became difficult. They descended through various zones of the ocean, watching as bioluminescent creatures flashed past their window, gradually disappearing as they went deeper than any light-producing organism lived. At around 30,000 feet, about 6,000 feet from the bottom, they heard a loud crack. One of the external viewing ports had fractured. Not the main port that they were looking through, but an external port in the entrance tunnel. This was a serious problem. If the crack worsened, if the port failed completely, the pressure could potentially cause a catastrophic failure of the entire vessel. Pickard and Walsh had to make a decision. They could abort the dive, releasing their ballast and returning to the surface, or they could continue and hope that the damage wouldn't get worse. After a tense discussion, they decided to continue. They had come too far to turn back now. At approximately 1 p.m. local time, after 4 hours and 48 minutes of descent, the Trieste touched down on the bottom of Challenger Deep at a depth of approximately 35,814 feet, or about 6.8 miles. They had reached a place where no human had ever been. A place more remote than the surface of the moon would be 9 years later. The pressure outside the sphere was over 16,000 pounds per square inch, more than 1,000 times atmospheric pressure. If the sphere had failed, death would have been instantaneous. Through their small viewing port, obscured somewhat by sediment their landing had disturbed, Pickard and Walsh observed the bottom of the trench. What they saw would change scientific understanding forever. They saw a flat, muddy bottom, but more importantly, they saw life. Pickard described seeing what appeared to be a flatfish, about a foot long, resembling a sole or flounder lying on the bottom. They also observed what looked like shrimp. These sightings, though brief and somewhat unclear due to the disturbed sediment, proved definitively that complex life could exist even at the deepest point in the ocean. The theory that life couldn't exist below a certain depth was shattered in that moment. They spent only 20 minutes on the bottom. The damaged port made them cautious about staying longer, and they had limited life support in the sphere. After taking measurements and observations, they released their ballast and began the ascent. The return journey took 3 hours and 27 minutes, faster than the descent, because they were rising under buoyancy rather than falling under gravity with controlled descent. When they surfaced, they had completed one of the greatest exploration achievements in human history, comparable to reaching the poles or climbing Mount Everest. The findings from the Trieste dive were significant, but limited by the brief duration and the primitive observation equipment available at the time. They had confirmed that life existed at full ocean depth. They had measured the temperature as slightly above freezing, and they had collected some water samples. But the dive raised as many questions as it answered. What other creatures lived down there? How did they survive? What did they eat? How did the ecosystem function? These questions would remain largely unanswered for decades because no one returned to Challenger Deep for over 50 years. Why the long gap? Several factors contributed. First, the Trieste dive had demonstrated that reaching the bottom was possible, but it had also shown how dangerous and difficult it was. The technology of the time was barely adequate, and there was no margin for error. Second, funding for deep ocean exploration decreased after the early 1960s as public and government attention shifted to space exploration. The space race was in full swing, and resources flowed toward putting humans on the moon rather than at the bottom of the ocean. Third, there was a perception that the deep ocean was relatively uniform and uninteresting, a vast expanse of mud with little variation. This perception was wrong, as later research would show, but it influenced funding decisions for decades. Throughout the 1970s, 80s, and 90s, deep ocean research continued, but it focused primarily on the abyssal plains at depths of 10,000 to 20,000 feet and on hydrothermal vents at mid-ocean ridges. These areas were easier to access and were yielding exciting discoveries. The Hadal Zone, including the Mariana Trench, remained largely unexplored. Remotely operated vehicles and autonomous landers occasionally visited these depths, but no humans returned to Challenger Deep. This changed in the early 2000s when filmmaker and explorer James Cameron became interested in deep ocean exploration. Cameron had directed the movie Titanic, which required extensive underwater filming, and he had developed a passion for the ocean and its mysteries. He began to dream of returning to Challenger Deep, but he wanted to do more than just touch the bottom briefly, as Pickard and Walsh had done. He wanted to explore, to film in high definition, to collect samples, and to spend significant time at depth. This would require building an entirely new submersible using modern technology. Cameron assembled a team of engineers, scientists, and technicians, and over the course of several years, they designed and built the Deep Sea Challenger. This submersible was dramatically different from the Trieste. It was more compact, shaped like a vertical torpedo, and designed for a single pilot. The pressure sphere was made of steel over 2.5 inches thick, and the entire vessel was packed with cameras, lights, sampling equipment, and scientific instruments. It was painted a bright green color for visibility, and named to reflect its purpose of challenging the deep sea. The Deep Sea Challenger underwent extensive testing in progressively deeper waters, first in shallow depths, then down to a few thousand feet, then to over 26,000 feet in the New Britain Trench near Papua New Guinea. Each test provided data that allowed the team to refine the systems and procedures. Finally, in March 2012, Cameron and his team traveled to the Mariana Trench aboard the support ship Mermaid Sapphire. The moment had arrived. On March 26, 2012, Cameron climbed into the Deep Sea Challenger and began his descent. Unlike the Trieste, which took nearly 5 hours to reach the bottom, the Deep Sea Challenger completed the journey in just 2 hours and 36 minutes. The vessel was more streamlined and used a more efficient descent profile. Cameron documented the entire journey with multiple cameras, capturing high-definition footage of the descent through the water column. He filmed bioluminescent creatures, observed the transition from the midnight zone to the Hadal zone, and watched as the last traces of any life in the water column disappeared. When he touched down on the bottom of Challenger Deep at a depth of approximately 35,756 feet, Cameron became the third person to reach this point and the first to do so solo. But his mission was just beginning. He spent several hours on the bottom, far longer than Pickard and Walsh had been able to stay. He piloted the submersible across the seafloor, covering a significant distance and filming everything he saw. The high-definition cameras captured stunning footage of the bottom environment, showing the fine sediment, small hills and depressions, and the occasional rock or harder surface. Cameron observed amphipods, those giant crustaceans we discussed earlier, swarming around the submersible, attracted by the lights and perhaps by chemical cues from the vehicle. He collected samples of these creatures using a slurp gun, essentially an underwater vacuum system. He also collected sediment samples and water samples at various depths during the descent and ascent. The submersible's cameras captured footage of xenophyophores, those large single-celled organisms sitting on the sediment surface like delicate lacework. One of the most important aspects of Cameron's dive was what he didn't see. He didn't observe any fish at the very bottom of Challenger Deep. He saw amphipods, he saw microbial mats in the sediment, he saw xenophyophores, but no fish. This was significant because Pickard and Walsh had reported seeing what appeared to be a flatfish. Cameron's more extensive observations suggested that fish might be extremely rare or absent at the absolute deepest point, though they're found at slightly shallower depths within the trench. This sparked debate among scientists about whether the original Trieste observation had been accurate, or whether what Pickard and Walsh saw had been misidentified. Perhaps a sea cucumber that resembled a fish in the poor visibility. Cameron also made an unfortunate discovery during his dive. He observed what appeared to be a plastic bag on the bottom of Challenger Deep. This was one of the first documented sightings of human pollution at the deepest point on Earth, a sobering reminder that human impact has reached even the most remote places on the planet. This observation would later be confirmed by other expeditions that found microplastics and chemical pollutants in trench sediments and organisms. The Deep-Sea Challenger mission was extensively documented, resulting in a feature film, a scientific documentary, and numerous research papers. The samples collected during the dive and subsequent dives by other researchers have been studied extensively. The amphipods collected showed incredibly high levels of piezolites, particularly TMAO, confirming the biochemical adaptations necessary for life at extreme depth. The sediment samples contained diverse microbial communities, with genetic analysis revealing thousands of distinct bacterial and archaeal species, many of them previously unknown. Cameron's dive reignited interest in Hadal exploration and demonstrated that modern technology could make repeated trips to full ocean depth feasible. His success inspired others to develop their own deep-diving submersibles. One person particularly inspired was Victor Vescovo, a former Navy officer and private equity investor with a passion for exploration. Vescovo had climbed the highest mountain on each continent and had skied to both the North and South Poles. He decided that his next challenge would be to dive to the deepest point in each of the world's 5 oceans, a feat that had never been accomplished. Vescovo partnered with Triton Submarines, a company specializing in building submersibles for research and tourism, to design and build a submersible capable of repeated dives to full ocean depth. The result was the DSV limiting factor, named after a concept in mathematics and engineering relating to the maximum capacity of a system. The limiting factor was designed to be the most capable deep-diving submersible ever built, unlike the Deep-Sea Challenger, which was designed for a single pilot and was essentially retired after Cameron's dives. The limiting factor was designed for 2 people and for repeated use. It featured a titanium pressure sphere 3.5 inches thick, capable of withstanding the pressure at any point in the ocean with a significant safety margin. The submersible was equipped with state-of-the-art cameras, sonar mapping equipment, robotic arms for sample collection, and life support systems that could sustain 2 people for up to 96 hours in an emergency, though normal dives lasted around 12 hours. It was designed to be deployed from a ship and recovered repeatedly without requiring extensive maintenance between dives. This was a significant advance over previous deep-diving vehicles. In 2019, Vescovo and his team embarked on the 5 Deeps expedition, with the goal of diving to the deepest point in each ocean: the Puerto Rico Trench in the Atlantic, the South Sandwich Trench in the Southern Ocean, the Java Trench in the Indian Ocean, the Challenger Deep in the Pacific, and the Malloy Deep in the Arctic Ocean. The expedition was supported by a research vessel, the DSSV Pressure Drop, which carried the limiting factor and its support equipment. Between April and August 2019, Vescovo successfully completed dives to all 5 of the deepest points, becoming the first person to visit the bottom of each ocean. The dive to Challenger Deep took place on April 28, 2019. Vescovo reached a depth of 35,843 feet, slightly deeper than Cameron's measurement, and he would return to the trench multiple times over the following months, completing a total of 4 dives to Challenger Deep. The findings from the limiting factor expeditions were extensive. The submersible's high-resolution sonar allowed for detailed mapping of large sections of the trench floor, revealing topographic features that had never been clearly seen before. The team discovered that Challenger Deep is not a flat plain, but has significant topographic variation, with hills, valleys, and what appear to be fault scarps where the ocean floor has fractured and shifted. The precise depth of the deepest point is still being debated based on these new measurements, with some readings suggesting depths of up to 36,070 feet in certain spots. Vescovo collected numerous biological samples from the bottom, including amphipods, holothurians or sea cucumbers, and sediment cores containing diverse microbial communities. The amphipods collected were sent to laboratories around the world for analysis. Studies of these creatures revealed new species and provided detailed information about their genetics, biochemistry, and physiology. One study found that hadal amphipods have evolved unique mutations in genes related to DNA repair, possibly as an adaptation to the higher levels of naturally occurring radiation in the deep ocean, where radioactive elements in the sediment are more concentrated. The expedition also made systematic measurements of water chemistry at various depths, documenting how temperature, salinity, oxygen concentration, and pH change from the surface to the bottom. These measurements provide baseline data that future expeditions can compare against to detect any changes over time, whether from natural variability or from human-caused impacts like climate change and ocean acidification. Perhaps most disturbingly, the limiting factor expeditions confirmed and expanded on Cameron's observations of pollution. Vescovo reported seeing what appeared to be candy wrappers and a plastic bag at the bottom of Challenger Deep. Sediment samples collected during the dives contained microplastics, tiny fragments of plastic less than 5 millimeters in size. Analysis of amphipods collected from the trench found high concentrations of persistent organic pollutants, including chemicals that have been banned for decades but persist in the environment. These pollutants are being transported from land and surface waters down to the deepest ocean through the sinking of particles and through the food web, accumulating in the tissues of deep-sea organisms. One of the most valuable aspects of the limiting factor program is that, unlike previous deep-diving submersibles, this one continues to operate. After the 5 Deeps expedition, Vescovo has used the submersible for additional scientific dives, including returning to the Mariana Trench multiple times. In 2020, he invited scientists, including renowned ocean researcher Dr. Kathy Sullivan, the first American woman to walk in space, to dive with him to Challenger Deep. Sullivan's dive made her the first woman and the first astronaut to reach the deepest point in the ocean, and at age 68, she became the oldest person to make the journey. The submersible has also been used to explore other trenches and deep ocean features. Each dive adds to our knowledge and provides opportunities to test new equipment and techniques. The limiting factor has demonstrated that routine access to full ocean depth is now possible, at least for those with sufficient resources. This has led to discussions about making deep ocean exploration more accessible to the scientific community, perhaps through partnerships where research institutions can purchase time on the submersible for their own projects. In addition to crewed submersibles, remotely operated vehicles and autonomous landers have continued to visit the Mariana Trench, providing complementary data to the crewed missions. The Chinese remotely operated vehicle Haidu-1 has completed multiple dives to the trench, reaching depths of over 33,000 feet and collecting samples. Japanese research teams have deployed landers equipped with cameras and bait that can remain on the bottom for extended periods, capturing footage of hadal organisms going about their normal behaviors without the disturbance of a submersible's lights and movements. One particularly interesting finding from lander-based research has been the documentation of feeding frenzies when food falls arrive. When researchers have deployed large bait, such as mackerel or tuna carcasses, cameras have recorded hundreds of amphipods arriving within hours, swarming over the food and stripping it to bones. These observations show that hadal scavengers are highly efficient at detecting and exploiting food sources, even though such sources are rare. The amphipods appear to have extremely sensitive chemoreceptors that can detect organic chemicals in the water from great distances, allowing them to locate food quickly in the vast darkness of the trench. Another important finding from recent expeditions has been the discovery of significant bacterial activity in trench sediments. Microbiologists analyzing sediment cores have found that bacteria are not just present, but metabolically active, meaning they're alive and carrying out life processes. Some of these bacteria are breaking down complex organic molecules, including hydrocarbons. Others are involved in cycling nitrogen, sulfur, and other elements. This microbial activity is crucial for nutrient cycling in the trench ecosystem. Without these bacteria, organic matter would accumulate in the sediment, and nutrients would be locked away, unavailable to other organisms. Recent research has also focused on the geological activity of the trench. The Mariana Trench is an active subduction zone, meaning one tectonic plate is being pushed beneath another. This process generates earthquakes, some of them quite powerful. Scientists have deployed seismometers on the ocean floor in and near the trench to study these earthquakes and to understand the mechanics of subduction. These studies have revealed that the subduction process is more complex than previously thought, with some areas of the descending plate releasing water and other fluids that rise up into the overlying plate, potentially triggering earthquakes and influencing the chemistry of the trench environment. There's also been research into mud volcanoes in the trench. These are mounds on the ocean floor where liquid mud, gas, and sometimes solid fragments are erupted from deep beneath the seafloor. Scientists have discovered several of these features in the Mariana Trench, and they're of interest both geologically and biologically. The fluids emerging from mud volcanoes can contain methane, hydrogen sulfide, and other chemicals that microorganisms can use as energy sources. Around some mud volcanoes, researchers have found dense microbial communities and even larger organisms like clams and mussels that host symbiotic bacteria. The collective findings from all these expeditions, from the Trieste in 1960 to the limiting factor missions of recent years, have fundamentally transformed our understanding of the deep ocean. We now know that the Hadal Zone is not a uniform, lifeless abyss, but a complex mosaic of different habitats, each with its own community of specially adapted organisms. We know that life can exist and even thrive at the absolute limits of pressure that liquid water can maintain. We know that the deep ocean is connected to surface processes through the sinking of organic matter, the circulation of water masses, and unfortunately, through the transport of pollutants. These expeditions have also revealed how much we still don't know. Despite all the dives, all the samples collected, all the footage recorded, we've only explored a tiny fraction of the Mariana Trench. The vast majority of its extent remains unmapped and unobserved. Each expedition raises new questions. How do Hadal organisms find mates in the vast darkness? How long do they live? How do their populations respond to natural variability in food supply? How are they being affected by human activities like deep-sea mining, pollution, and climate change? Are there entire groups of organisms that we haven't yet discovered because they're rare, localized, or simply live in areas we haven't yet visited? The legacy of these expeditions extends beyond the specific findings about the Mariana Trench. They've demonstrated that human ingenuity and determination can overcome seemingly impossible challenges. They've shown that exploration is still possible in the 21st century, that there are still frontiers to be crossed and discoveries to be made on our own planet. They've inspired a new generation of engineers, scientists, and explorers to turn their attention to the ocean, which remains far less explored than outer space, despite being much more accessible. The technology developed for these deep diving missions has applications beyond exploration. The materials and engineering techniques used to build pressure spheres capable of withstanding extreme pressure have been adapted for other uses, from industrial applications to medical devices. The sensors and cameras developed for deep-sea use have improved capabilities for underwater archaeology, underwater construction, and environmental monitoring. The life support systems and communication systems have informed designs for other enclosed environments, including spacecraft and undersea habitats. Looking forward, the next frontier in Hadal exploration will likely involve longer duration missions and permanent or semi-permanent monitoring stations. Imagine a network of automated observatories on the floor of the Mariana Trench, equipped with cameras, sensors, and sampling equipment, continuously recording data and streaming it to researchers around the world. Such a system would allow scientists to observe how Hadal ecosystems change over time, to document rare events like whale falls landing on the bottom, and to detect early signs of environmental change. The technology to build such a system exists today. What's needed is funding and international cooperation to make it a reality. There are also proposals for human habitats on the ocean floor at more moderate depths, perhaps a few thousand feet down, which could serve as staging areas for expeditions to greater depths. While living at the bottom of the Mariana Trench is not feasible with current technology due to the extreme pressure, a habitat at intermediate depth could allow researchers to spend extended periods studying the deep ocean without the need to return to the surface after each dive. Such facilities would be similar in concept to the International Space Station, providing a permanent human presence in an extreme environment for scientific research. The missions to Challenger Deep and the broader exploration of the Mariana Trench represent humanity at its best: curious, ambitious, collaborative, and determined to understand our world. Each expedition builds on the work of those who came before, adding pieces to an enormous puzzle. The Trieste showed that reaching the bottom was possible and that life existed there. The Deep-Sea Challenger showed that modern technology could bring cameras and sophisticated instruments to depth, revealing the environment in unprecedented detail. The limiting factor showed that repeated missions to full ocean depth are achievable, making systematic exploration feasible. Future missions will add even more, gradually filling in our understanding of this remarkable place. The deep ocean, and the Mariana Trench in particular, reminds us that Earth is still a planet of mysteries. After thousands of years of human civilization, after decades of space exploration, after the mapping of the human genome and the splitting of the atom, there are still places on our own planet that are virtually unknown. The creatures living in the Mariana Trench have been evolving and adapting for millions of years in an environment we're only beginning to understand. They have lessons to teach us about adaptation, survival, and the incredible diversity of life. And somewhere in the darkness, in the cold and crushing pressure, there are almost certainly organisms we haven't yet discovered, living lives we can barely imagine, waiting for the next submersible to descend and reveal their existence to the world above. The Mariana Trench, being the most extreme and least accessible environment on Earth, has naturally become a focal point for mystery and speculation. When humans venture into places where no one has gone before, where visibility is limited and our understanding is incomplete, it's inevitable that we encounter things we can't immediately explain. Some of these mysteries have been solved through further research and investigation. Others remain open questions that continue to puzzle scientists. And still others have been embellished and exaggerated by popular imagination, transforming scientific curiosities into legends and myths. Let's explore what has actually been recorded at the bottom of the Mariana Trench and separate fact from fiction, while acknowledging that in such an extreme and poorly explored environment, there's always room for genuine mystery. Let's begin with sounds, because the ocean is far from silent, and the deep ocean has produced some of the most mysterious acoustic phenomena ever recorded. Sound travels exceptionally well through water, much better than through air, and it can travel for hundreds or even thousands of miles through the ocean. Scientists use hydrophones, underwater microphones, to monitor ocean sounds for various purposes, including tracking whale populations, monitoring seismic activity, and detecting submarines. Over the decades, hydrophones have picked up numerous unexplained sounds from the deep ocean, some of which have originated from the vicinity of deep trenches, including the Mariana Trench. One of the most famous mysterious sounds from the deep ocean is called the bloop. This sound was detected by the National Oceanic and Atmospheric Administration, or NOAA, in 1997. The bloop was an ultra-low frequency sound that was powerful enough to be detected by sensors more than 3,000 miles apart. The sound lasted for about 1 minute and had a pattern that rose rapidly in frequency, creating a characteristic profile that scientists described as similar to vocalizations made by living creatures, but much, much louder. The bloop was detected in the southern Pacific Ocean, not directly from the Mariana Trench, but its mysterious nature and enormous volume led to widespread speculation about what could have produced it. Many theories were proposed. Some scientists suggested it might be an unknown species of giant marine animal, something even larger than a blue whale. The blue whale is the largest animal ever known to exist on Earth, reaching lengths of up to 100 feet and weights of 200 tons, and its vocalizations are among the loudest sounds produced by any animal. But the bloop was far louder than any whale vocalization ever recorded. Could there be something even larger in the deep ocean? The speculation captured public imagination, with suggestions ranging from unknown species of colossal squid to prehistoric survivors like plesiosaurs or megalodon sharks that somehow still existed in the deep ocean trenches. However, the mystery of the bloop was eventually solved through careful analysis. In 2005, NOAA scientists determined that the sound was most likely produced by an ice quake, which is the fracturing and cracking of large icebergs or ice shelves. When massive pieces of ice fracture, they produce extremely loud sounds that can travel vast distances through the ocean. The location of the bloop, when traced back to its source, was consistent with areas where large icebergs from Antarctica were present. The frequency pattern of the sound, when analysed in detail, matched what would be expected from ice fracturing rather than from biological sources. While this explanation is less exciting than a giant unknown creature, it's supported by solid scientific evidence. But the bloop is not the only mysterious sound recorded in the ocean. There have been other unexplained acoustic phenomena detected over the years. In 1997, the same year as the bloop, another sound called the upsweep was detected. This sound is a long series of narrow-band upsweeping tones that has been detected seasonally and continues to be detected, though with decreasing intensity over time. The upsweep appears to originate from the Pacific Ocean, and while its exact source has not been definitively identified, scientists believe it's likely geological in origin, possibly related to volcanic activity on the seafloor. The Pacific Ocean has numerous underwater volcanoes and hydrothermal vents that could produce such sounds. Another sound, called the whistle, was recorded multiple times in the 1990s. This sound consisted of a series of narrowband components that lasted for several seconds and appeared to come from deep in the Pacific Ocean. Like the upsweep, the whistle's source has not been conclusively identified, but geological activity remains the most likely explanation. The ocean floor, particularly in tectonically active areas like trenches and mid-ocean ridges, is constantly shifting, fracturing, and releasing gases and fluids. These processes can produce a wide variety of sounds, specifically related to the Mariana Trench. There have been recordings of what some have called strange or unusual acoustic activity. However, it's important to understand that the trench is a geologically active area. The Pacific Plate is being subducted beneath the Mariana Plate, a process that generates frequent earthquakes. These earthquakes produce sounds that can be detected by hydrophones. The grinding of rock against rock, the fracturing of the descending plate, and the movement of fluids through fractures in the rock all create acoustic signatures. Additionally, there are mud volcanoes in the trench that periodically erupt, releasing gas and liquid mud. These eruptions can produce sounds ranging from low rumbles to sharp pops. Some of the sounds detected near the Mariana Trench have been attributed to military activity. The waters around Guam and the Mariana Islands are used by the United States Navy for various operations, including submarine exercises. Submarines, surface ships, and underwater explosives used in testing can all produce sounds that might be detected by monitoring equipment. Without access to classified military information, it can be difficult for civilian researchers to distinguish between natural sounds and those produced by military activities. There have also been reports of what some describe as biological sounds from the trench that don't match known species. However, these reports need to be approached with skepticism. The deep ocean does contain many species that produce sounds, including various fish and marine mammals. Some deep-sea fish can produce sounds by vibrating their swim bladders, though hadalfish don't have swim bladders. Whales and dolphins produce a wide variety of vocalizations, and while they don't live in the trench permanently, they can dive to significant depths, and their sounds can travel far through the ocean. Additionally, as we discussed earlier, there are likely many undiscovered species in the trench, and some of these might produce sounds that we haven't documented yet. However, any claim of mysterious biological sounds needs to be backed by solid recordings and analysis, not just anecdotal reports. Now let's turn to physical objects and anomalies observed at the bottom of the Mariana Trench. As we've mentioned in previous discussions, one of the most disturbing findings from recent expeditions has been the presence of human-made debris and pollution. Victor Vescovo's dives in the limiting factor documented what appeared to be a plastic bag, candy wrappers, and other debris at the bottom of Challenger Deep. James Cameron also reported seeing what looked like a plastic bag during his dive in 2012. These objects are not mysterious in the sense of being unexplained. Their origin is clear. They're pollution from human activities. But their presence at the deepest point on Earth is certainly anomalous in the sense that it's surprising and disturbing that human waste has reached this remote location. The mechanism by which these objects reach the bottom is not fully understood. Plastic debris in the ocean typically floats or is suspended in the water column, gradually breaking down into smaller pieces called microplastics. However, some plastic objects can become fouled with marine organisms or can absorb water and other materials that make them denser, causing them to sink. Additionally, plastic particles can be ingested by marine organisms and then transported downward through the food web and through fecal pellets, eventually reaching the ocean floor. The fact that intact plastic bags have been observed at the bottom suggests that they may have been weighted down by something or may have been protected from degradation during their descent. There have also been reports of what appear to be unusual geological features at the bottom of the trench. The high-resolution sonar mapping conducted during recent expeditions has revealed that the trench floor is not uniform but has considerable topographic variation. There are hills, valleys, fault scarps where the rock has fractured and shifted, and what appear to be channels where sediment may flow, or where fluids may seep from beneath the seafloor. Some of these features have raised questions among geologists about the processes that formed them. One particularly interesting feature is the presence of what appear to be impact craters on the floor of the trench. While these have not been definitively identified as such, some scientists have speculated that they could be the result of large objects falling from above, perhaps whale bones or other dense materials that have impacted the soft sediment with enough force to create depressions. Alternatively, they could be volcanic features, places where gas or fluid has erupted from below, creating circular depressions. More research is needed to determine the origin of these features. There have also been observations of unusual coloration in the sediment. In some areas, the sediment appears to have patches of different colors, ranging from white to gray to reddish-brown. These color variations are likely due to differences in sediment composition and the presence of different minerals or microbial communities. For example, areas where iron-rich fluids seep from the seafloor may have reddish sediment due to iron oxide, essentially rust. Areas with high microbial activity may have different colors due to pigments produced by the bacteria. However, without detailed sampling and analysis, it's difficult to determine exactly what's causing these color variations, and they remain somewhat of a mystery. One of the more intriguing aspects of exploration in the Mariana Trench is the occasional observation of what explorers describe as unexpected or out-of-place objects. During his dive, James Cameron reported seeing a rock or hard surface that appeared unusual compared to the surrounding soft sediment. Such rocks could have various origins. They might be pieces of the underlying bedrock that have been exposed by currents or landslides. They might be manganese nodules, which are mineral concretions that form slowly on the ocean floor over millions of years. Or they could be pumice from underwater volcanic eruptions that has become waterlogged and sunk. Without being able to collect samples and analyze them, it's impossible to say for certain what these objects are. There have been persistent rumors and claims, mostly on the internet and in popular media, of more sensational discoveries in the Mariana Trench. These include claims of ancient structures, megalithic monuments, crashed spacecraft, or evidence of lost civilizations. It's important to state clearly that there is no credible scientific evidence for any of these claims. The Mariana Trench is approximately 180 million years old, far older than human civilization. The trench formed through the subduction of tectonic plates, a natural geological process. Any structures built by ancient civilizations would be on land or in shallow coastal waters, not at the bottom of a deep ocean trench. Similarly, there's no evidence of extraterrestrial spacecraft or artifacts in the trench. Such claims typically originate from misinterpretation of images deliberate hoaxes, or pure fiction. However, there is one legitimate area where human-made objects exist at the bottom of the Mariana Trench: shipwrecks and military debris. The waters around the Mariana Islands saw significant naval combat during World War II, particularly the Battle of the Philippine Sea in 1944 and the Battle of Leyte Gulf, which involved fighting in waters relatively close to the trench. While most shipwrecks from these battles are at shallower depths where the combat actually occurred, it's possible that some debris from damaged ships could have drifted and sunk into deeper water. Additionally, the area has been used for military exercises and weapons testing for decades, and there could be unexploded ordnance or other military hardware on the trench floor. However, at the extreme depths of the Hadal zone, such objects would be very difficult to locate and would likely be covered by sediment. Unusual readings and measurements have also been reported from the Mariana Trench. During the Trieste dive in 1960, Piccard and Walsh reported that their instruments showed unexpected readings at certain depths. Some of these anomalies were later attributed to equipment malfunction or to the extreme conditions affecting the instruments in ways that hadn't been anticipated. Early deep-sea instruments were not always reliable under extreme pressure, and temperature variations could cause readings to drift or become inaccurate. Modern instruments are much more robust and are extensively tested before deployment, but even today, instruments can occasionally produce anomalous readings that require careful interpretation. One type of anomaly that has been documented is localized variations in water temperature. While the bottom water in the Mariana Trench is generally a uniform 1 to 4 degrees Celsius, there are areas where the temperature is slightly higher or lower than the surrounding water. These variations are typically small, just a degree or two, but they can indicate the presence of hydrothermal vents or cold seeps where fluids from beneath the seafloor are entering the ocean. Scientists are very interested in finding and studying these features because they support unique ecosystems and provide insights into the chemical exchanges between the Earth's interior and the ocean. Another type of anomaly involves variations in water chemistry. Instruments have detected localized areas where the concentration of certain chemicals, such as methane, hydrogen sulfide, or dissolved metals, is elevated compared to the surrounding water. These chemical anomalies are indicators of geological activity, such as the seepage of fluids from the subducting plate or from mud volcanoes. In some cases, these chemical signatures can be detected from a distance, allowing scientists to locate interesting geological features without having to search randomly across the vast trench floor. There have also been reports of unusual magnetic readings from certain areas of the trench. The Earth has a magnetic field, and rocks containing magnetic minerals can create localized variations in the magnetic field strength and direction. Underwater lava flows, which are common near mid-ocean ridges and volcanic areas, often have strong magnetic signatures. In the Mariana Trench, magnetic anomalies could indicate the presence of volcanic rocks, possibly from ancient underwater eruptions, or they could be related to the composition of the subducting plate. Some scientists have speculated that localized magnetic anomalies could even be caused by high concentrations of certain minerals in the sediment, though this is less common. One particularly fascinating area of ongoing research involves what scientists call deep-sea gigantism and its potential connection to unknown species. Deep-sea gigantism is a phenomenon where organisms living in the deep ocean grow to much larger sizes than their shallow water relatives. We've already discussed giant amphipods and the large single-celled xenophyophores, but there are other examples throughout the deep ocean. Giant isopods, which can reach lengths of over 16 inches, are found in the deep sea. Giant squid and colossal squid, some of the largest invertebrates on Earth, live at depths of 1,000 to 6,000 feet or deeper. Tube worms at hydrothermal vents can grow to 8 feet long. The reasons for deep-sea gigantism are not fully understood, but several factors may contribute. The cold temperatures slow metabolism, which could allow organisms to live longer and grow larger over their lifetimes. The high pressure may favor larger body sizes for reasons related to surface area to volume ratios and metabolic efficiency. The scarcity of food may favor larger organisms that can store more energy reserves and can travel farther to find food. Whatever the causes, the phenomenon raises an intriguing question. Could there be even larger organisms in the Hadal zone that we haven't yet discovered? Could there be truly giant creatures, larger than anything we've documented, living in the deepest parts of the trench? While it's tempting to imagine kraken-like monsters lurking in the abyss, the reality is that extremely large organisms require substantial amounts of food energy to survive. The Hadal zone, with its limited food supply, is not an ideal environment for giants. The largest organisms documented at extreme depth are the giant amphipods at around 12 inches, which is large for an amphipod, but not enormous in absolute terms. Fish at Hadal depths tend to be small, typically less than a foot long. The largest organisms in the trench are probably not much bigger than what we've already observed. However, this doesn't completely rule out the possibility of rare, large creatures. The ocean is vast, and rare species can easily avoid detection for long periods. There's also the question of bioluminescence, and the strange light patterns sometimes reported from the deep ocean. Bioluminescence is common in deep-sea organisms, with estimates suggesting that over 75% of deep-sea creatures can produce light. These organisms create light through chemical reactions, typically involving a molecule called luciferin and an enzyme called luciferase. The light produced can be blue, green, or occasionally red, and it's used for various purposes including attracting prey, finding mates, and startling predators. Some reports from deep-sea explorers describe seeing unusual patterns of bioluminescent light that don't match known species. For example, there have been descriptions of large, slowly moving patches of light or of coordinated flashing patterns that seem too organized to be random. While these observations are intriguing, they're difficult to study because bioluminescence is typically brief and unpredictable, and it's affected by the presence of submersibles and their lights. When a submersible with bright lights enters an area, many bioluminescent organisms will react by producing their own light, either as a startle response or as a defensive measure. This can create impressive light shows, but it also means that the behavior observed may not represent what happens under normal, undisturbed conditions. One specific mystery related to the Mariana Trench involves the so-called Mariana Trench Bridge, a term that has appeared in various internet discussions and conspiracy theories. According to these claims, there's a mysterious bridge-like structure at the bottom of the trench that some interpret as evidence of ancient advanced civilizations or extraterrestrial activity. However, investigation of these claims reveals that they're based on misinterpretation of bathymetric data, which is mapping of the seafloor topography. Sonar mapping can sometimes produce artifacts, apparent features that aren't actually there due to the way sonar data is processed and displayed. Additionally, natural geological features like ridges, faults, and channel systems can sometimes appear linear or structured in ways that might superficially resemble artificial constructions. But these are natural formations created by geological processes. There have also been claims about mysterious disappearances of ships or aircraft near the Mariana Trench, with some drawing parallels to the Bermuda Triangle. However, there's no statistical evidence that the waters around the Mariana Trench are more dangerous than other ocean areas. The Pacific Ocean is vast and heavily traveled by ships and aircraft, and unfortunately, accidents do occur due to weather, mechanical failure, human error, and other causes. The remoteness of the area and the depth of the ocean make it difficult to locate and recover wreckage when accidents do happen, which can contribute to a sense of mystery. But there's no evidence of any unusual phenomenon causing ships or aircraft to disappear specifically near the trench. It's worth addressing the question of military activity and secrecy surrounding the Mariana Trench. The Mariana Islands, including Guam, are strategic US territories with significant military presence. The waters around the islands are used for submarine operations, naval exercises, and weapons testing. This has led to speculation that the military knows more about the trench than they're publicly sharing. Perhaps even that they've discovered unusual things in the trench that are being kept classified. While it's true that some military operations are classified, there's no credible evidence of any extraordinary discoveries being hidden. The scientific expeditions to the trench have been civilian operations, and their findings have been published openly in scientific journals and presented in documentaries. If the military had discovered something truly extraordinary, it would be difficult to keep such information completely secret, given the number of people who would need to be involved. One final area of genuine scientific mystery involves the limits of life in the trench and the possibility of life existing in environments we haven't yet explored thoroughly. While we know that life exists at the bottom of Challenger Deep, there are still questions about whether life might exist even deeper within the sediment or within the rocks of the seafloor itself. Scientists have discovered microbial life in deep subsurface environments on land, sometimes miles below the surface, living in cracks and pores in rocks and surviving on chemical energy from geological processes. It's possible that similar deep biosphere ecosystems exist beneath the Mariana Trench, with microorganisms living in the subducting plate or in the overlying rocks. If such life exists, it would be extremely difficult to access and study, requiring deep drilling from the ocean floor, which is technically challenging and expensive. There's also the question of whether extremophile organisms, microbes that thrive in extreme conditions, might exist in the trench with metabolic capabilities we haven't yet documented. For example, there could be organisms that can survive even higher pressures than those at Challenger Deep, organisms that could potentially survive in the high-pressure ices that might exist in the deep interiors of icy moons like Europa. There could be organisms that use novel biochemistry, perhaps based on different molecules than the proteins and DNA that all known Earth life uses. Such discoveries would be revolutionary for biology and would expand our understanding of what life is and where it can exist. In summary, while the Mariana Trench has certainly produced its share of mysteries and anomalies, most of these have prosaic explanations rooted in natural geological and biological processes. The mysterious sounds detected in the ocean are typically from icebergs, earthquakes, volcanic activity, or marine animals. The unusual objects seen at the bottom are mostly human pollution, though there may also be natural geological features that are not yet fully understood. The unusual readings and measurements typically reflect real variations in the environment, such as temperature or chemical changes associated with geological activity. And while there are almost certainly undiscovered species in the trench, there's no credible evidence of ancient ruins, alien artifacts, or sea monsters. That said, the Mariana Trench remains a place of genuine mystery simply because we've explored so little of it. Every expedition brings surprises, whether it's a new species, an unexpected geological feature, or a previously unknown behavior of known organisms. The deep ocean has taught us to expect the unexpected, and it would be premature to assume we know everything about what exists in the trench. The most exciting mysteries may not be the sensational claims of conspiracy theories, but the quiet discoveries waiting to be made by the next generation of explorers and scientists, new species with remarkable adaptations, new ecosystems based on chemical energy, new insights into the limits of life and the processes that shape our planet. These are the real mysteries of the Mariana Trench, and they're more than exciting enough to capture our imagination without needing embellishment or exaggeration. The discovery of human pollution at the bottom of the Mariana Trench represents one of the most sobering revelations of modern deep-sea exploration. When Victor Vescovo descended to Challenger Deep in 2019 and spotted what appeared to be a plastic bag and candy wrappers on the seafloor, when James Cameron made similar observations during his 2012 dive, these findings sent shockwaves through the scientific community and the public alike. Here was the most remote, inaccessible place on Earth, a location that had been visited by only a handful of humans in all of history, and yet human waste had somehow reached it. The presence of pollution in the Mariana Trench is not just an isolated curiosity. It's a stark indicator of how thoroughly human activity has permeated every corner of our planet, and it raises urgent questions about the scale of our environmental impact and what it means for the future of Earth's ecosystems. To understand how pollution reaches the Mariana Trench, we need to understand the interconnected nature of the ocean system. The ocean is not a collection of separate, isolated bodies of water. It's a single, global system where water, organisms, and unfortunately pollutants can move across vast distances. Ocean currents, both surface and deep, circulate water around the entire planet. The Great Ocean Conveyor Belt, also called thermohaline circulation, moves water from the surface to the deep ocean and back again over the course of centuries or millennia. Water that sinks in the North Atlantic or around Antarctica can eventually make its way to the deep Pacific Ocean and into trenches like the Mariana. But currents alone don't fully explain how pollution reaches the deepest parts of the ocean. After all, most plastic and other pollutants float at the surface or remain suspended in the upper layers of the ocean. The famous Great Pacific Garbage Patch, a massive accumulation of plastic debris in the North Pacific, floats at the surface. So how does this floating debris make its way 7 miles down to the bottom of the trench? The answer lies in several interconnected processes that transport material from the surface to the deep ocean. Let's start with the most visible form of pollution, macroplastics, which are larger pieces of plastic like bottles, bags, fishing nets, and packaging materials. Globally, it's estimated that between 8 and 12 million metric tons of plastic enter the ocean every year. That's the equivalent of dumping a garbage truck full of plastic into the ocean every single minute of every day. This plastic comes from many sources: littering on beaches and in rivers, improper waste management, industrial discharge, fishing gear that's lost or deliberately discarded, and plastic particles from worn vehicle tires that wash off roads into waterways. Most plastic, when first entering the ocean, floats because its density is less than that of seawater. Polyethylene and polypropylene, two of the most common plastics, have densities around 0.9 to 0.95 grams per cubic centimeter, while seawater has a density of approximately 1.025 grams per cubic centimeter. This means that fresh, clean plastic will float. However, several processes can change this and cause plastic to sink. First, plastic in the ocean becomes fouled with biological growth. Algae, bacteria, barnacles, and other marine organisms colonize the surface of plastic debris, a process called biofouling. This biological coating adds weight and increases the overall density of the plastic object. If enough organisms attach to a piece of plastic, it can become negatively buoyant, meaning it's denser than seawater, and it will begin to sink. A plastic bottle that would normally float can, after weeks or months at sea, become covered with enough marine growth that it sinks to the bottom. Second, plastic absorbs water and other substances over time. While plastic is often thought of as impermeable, it actually has a microscopic structure that can allow water molecules and other chemicals to penetrate into the material over long periods of exposure. This absorption increases the weight of the plastic. Additionally, plastic can adsorb, with a D, meaning chemicals in the seawater can stick to the surface of the plastic. Plastics are particularly good at absorbing oily, hydrophobic compounds like PCBs and other persistent organic pollutants. These adsorbed chemicals add mass to the plastic and can affect its buoyancy. Third, plastic degrades in the ocean, breaking down into smaller and smaller pieces. Ultraviolet radiation from the sun, wave action, and microbial activity all contribute to the degradation process. As plastic breaks into smaller fragments called microplastics, generally defined as pieces smaller than 5 millimeters, and eventually nanoplastics at sizes measured in nanometers, these particles can become more easily incorporated into marine snow, the constant rain of organic particles that falls from the surface ocean to the deep ocean floor. Marine snow is a crucial concept for understanding how pollutants reach the deep ocean. In the sunlit surface layers of the ocean, photosynthetic organisms like phytoplankton grow and reproduce. These tiny organisms are eaten by zooplankton and other creatures, which produce fecal pellets. Dead phytoplankton, dead zooplankton, molted shells, mucus, and other organic material all clump together into aggregates called marine snow. These aggregates are denser than seawater and slowly sink toward the ocean floor. The sinking rate varies depending on the size and composition of the particles, but typical rates are around 100 to 200 meters per day, which means it can take weeks or months for marine snow to reach the bottom of the Mariana Trench. Microplastics can become incorporated into marine snow in several ways. Zooplankton and other small marine animals can ingest microplastic particles, mistaking them for food. When these animals produce fecal pellets, the microplastics are included in the pellets, which then sink. Microplastics can also stick to organic particles through electrostatic forces or by becoming tangled in the sticky mucus that helps bind marine snow aggregates together. Once incorporated into marine snow, the microplastics are carried downward to the deep ocean. Studies have documented this process directly. Researchers have collected marine snow samples at various depths in the ocean and found microplastic particles embedded within them. The deeper they sampled, the more evidence they found of microplastics being transported downward. One study in the Mediterranean Sea found that microplastics can sink at rates of up to several hundred meters per day when incorporated into fast-sinking marine snow aggregates. This means that microplastics released at the surface can reach the seafloor in a matter of weeks, even in very deep locations. There's another process that can transport plastic to great depths: ingestion by deep-diving animals. Many marine animals, including whales, seals, sea turtles, and some fish, are capable of diving to significant depths. While none of these animals can reach the bottom of the Mariana Trench, they can dive to intermediate depths of several thousand feet. If these animals ingest plastic at the surface and then dive deep, they may excrete fecal material containing microplastics at depth. Additionally, when large marine animals die, their bodies sink to the ocean floor in what's called a whale fall or a fish fall. If these animals have microplastics in their tissues, those microplastics are transported to the deep ocean along with the carcass. Ocean currents also play a direct role in distributing pollution. While surface currents are well known and have been studied for centuries, deep ocean currents are less well understood, but equally important. The thermohaline circulation system, driven by differences in water temperature and salinity, moves water throughout the global ocean at all depths. Water that sinks in polar regions, becoming cold and dense, flows along the ocean bottom toward the equator, eventually rising again in other regions. This deep circulation can transport pollutants that have sunk to depth over long distances. Near the Mariana Trench specifically, there are additional factors that might concentrate pollutants. The trench is located in the western Pacific Ocean, not far from major population centers in Asia. Countries including China, Indonesia, Philippines, Vietnam, and Thailand are among the largest contributors to ocean plastic pollution, partly due to their large populations and developing waste management infrastructure. Plastic released from these countries can enter the ocean and be transported by currents toward the deeper parts of the Pacific, including the Mariana Trench area. Additionally, the geography of the trench itself may contribute to accumulation of debris. The trench is a depression in the ocean floor, essentially a long, narrow valley. Material settling from above might tend to accumulate in this depression rather than being evenly distributed across the seafloor. Think of it like debris accumulating in a ditch or a valley on land. Gravity causes material to move downhill into low points. The same principle applies on the ocean floor. Sediments, organic matter, and unfortunately pollutants may preferentially accumulate in the deepest parts of the trench. Now let's talk specifically about microplastics, because these are perhaps the most pervasive and concerning form of plastic pollution. Microplastics have been found in virtually every marine environment that's been studied, from the surface waters to the deepest trenches, from polar ice to tropical reefs. They've been found in the air we breathe, the water we drink, and the food we eat. Studies have detected microplastics in the tissues of marine organisms ranging from tiny zooplankton to large fish and marine mammals. And yes, they've been found in the Mariana Trench. In 2018, a study published in the journal Marine Policy reported finding microplastics in amphipods collected from 6 of the world's deepest ocean trenches, including the Mariana Trench. The amphipods were collected at depths ranging from 23,000 to 33,000 feet. When researchers examined the digestive systems of these creatures, they found microplastic fibers in 72% of the individuals. These fibers were identified as various types of plastic, including polyethylene, polyamide, polyvinyl, and others. Some individual amphipods had multiple plastic fibers in their guts. This finding was significant for several reasons. First, it demonstrated that microplastics have reached the deepest parts of the ocean and are being ingested by organisms living there. Second, it showed that hadal organisms are exposed to plastic pollution despite living in one of the most remote environments on Earth. Third, it raised questions about what effects these microplastics might have on deep-sea organisms and ecosystems. But microplastics aren't the only form of pollution found in the Mariana Trench. Perhaps even more disturbing is the discovery of persistent organic pollutants, or POPs, in hadal organisms. POPs are synthetic chemicals that are resistant to environmental degradation, meaning they persist in the environment for long periods. They include compounds like PCBs, which were used in electrical equipment and other applications, but were banned in most countries in the 1970s and 80s due to health concerns, and PBDEs, which are flame retardants used in furniture, electronics, and textiles. A groundbreaking study published in 2017 in the journal Nature Ecology and Evolution analyzed amphipods from the Mariana Trench and the Kermadec Trench in the South Pacific. The results were shocking. The hadal amphipods contained some of the highest levels of POPs ever recorded in marine organisms. The concentrations of PCBs in the amphipods were 50 times higher than in crabs living in heavily polluted rice paddies in China. The levels were comparable to or higher than those found in organisms from some of the most polluted areas on Earth, including industrialized estuaries and bays that have been contaminated by decades of industrial discharge. How did these chemicals reach the bottom of the ocean in such high concentrations? POPs are hydrophobic, meaning they don't dissolve well in water, but they do dissolve in fats and oils. They tend to accumulate in the fatty tissues of organisms, a process called bioaccumulation. As one organism eats another, the POPs are transferred up the food chain and become more concentrated at each level, a process called biomagnification. In the surface ocean, POPs become incorporated into organic matter and into the tissues of plankton and small fish. When this organic matter sinks as marine snow, or when dead organisms sink to the deep ocean, the POPs go with them. In the deep ocean, decomposition is slow due to the cold temperatures and low oxygen levels. Organic matter can persist for longer periods, and the POPs it contains can be released and potentially reabsorbed by other organisms. Amphipods and other scavengers feeding on this material ingest the POPs, which then accumulate in their fatty tissues. Because food is scarce in the hadal zone, and amphipods likely have slow metabolisms and long lifespans, they may accumulate POPs over many years, reaching very high concentrations. Additionally, because the deep ocean is a sink for sinking material, pollutants may become concentrated there, paradoxically making the most remote parts of the ocean some of the most polluted in terms of certain contaminants. The implications of this pollution are serious. POPs are toxic to living organisms. They can disrupt hormone systems, impair reproduction, damage immune function, and cause various other health problems. The effects of high POP concentrations on hadal organisms are not well understood, partly because these organisms are difficult to study in laboratory settings. But it's reasonable to be concerned that these chemicals could be harming deep-sea ecosystems in ways we don't yet fully comprehend. There's also the question of heavy metals and radioactive contamination. Some areas of the ocean floor contain elevated levels of heavy metals like mercury, lead, and cadmium, which can come from industrial discharge, mining activities, and natural sources like underwater volcanic activity. Radioactive isotopes from nuclear weapons testing in the mid-20th century and from accidents like the Fukushima nuclear disaster in 2011 have also entered the ocean. Studies have detected elevated levels of radioactive carbon-14 in deep-sea organisms, indicating that they're being exposed to anthropogenic radioactive contamination. One of the pathways for radioactive contamination to reach the deep ocean is through the same mechanisms that transport other pollutants, incorporation into marine snow and sinking organic matter. Radioactive isotopes can be absorbed by phytoplankton in the surface ocean and then transferred through the food web. When organisms die and sink, they carry these isotopes to the deep ocean. Studies of amphipods from the Mariana Trench have found elevated levels of carbon-14, which is produced both naturally by cosmic rays and artificially by nuclear weapons testing and accidents. The elevated levels indicate that these organisms have been exposed to bomb-derived radiocarbon, proving that even radioactive fallout from human activities has reached the deepest parts of the ocean. Beyond chemical pollutants, there's also the issue of marine debris of all types. Fishing gear, including nets, lines, and traps, is lost or discarded in the ocean in enormous quantities every year. This ghost gear can drift for long distances and can sink to the ocean floor. While most fishing doesn't occur at the extreme depths of the Mariana Trench, gear can be transported by currents or can sink after becoming fouled. Expeditions have found fishing line and other debris at depths of over 20,000 feet in various trenches. There's also military debris. The Pacific Ocean was the site of extensive naval warfare during World War II, and many ships and aircraft were sunk or damaged. Additionally, the ocean has been used for weapons testing and munitions disposal. After World War II, it was common practice to dispose of excess or obsolete munitions by dumping them in the ocean. Thousands of tons of conventional and chemical weapons were dumped in various ocean locations, including some areas of the Pacific. While most of this dumping occurred at more moderate depths rather than in the deepest trenches, there's concern that corroding munitions could be leaking toxic materials that eventually make their way to the deep ocean. Ship traffic also contributes to pollution through various pathways. Ships release oil, fuel, and other chemicals into the water, both through accidental spills and through routine operations. Ballast water, which ships take on and discharge to maintain stability, can transport organisms and pollutants from one part of the ocean to another. Anti-fouling paints used on ship hulls contain toxic chemicals designed to prevent marine organisms from attaching to the hull, and these chemicals leach into the water. Ships also produce noise pollution, which can affect marine life, though the deep trenches are likely relatively shielded from surface ship noise. Air pollution also plays a role in ocean contamination. Chemicals released into the atmosphere can be transported by winds over long distances and eventually deposited into the ocean through rainfall or by directly settling out of the air. Mercury from coal-burning power plants, for example, can be emitted into the atmosphere, transported globally, and deposited into the ocean, where it can be converted into toxic methylmercury and accumulate in marine food webs. Similarly, POPs can evaporate from contaminated soils or water in one part of the world, be transported through the atmosphere, and deposited into the ocean in a completely different region. This process of global transport and deposition means that pollution generated in one country can affect marine ecosystems on the other side of the planet. The presence of pollution in the Mariana Trench tells us several important things. First, it demonstrates that there is no pristine, untouched wilderness left on Earth. Even the most remote environments have been affected by human activities. The romantic notion of the deep ocean as a final frontier, a place beyond human reach and impact, has been proven false. Our civilization's footprint is global and comprehensive. Second, it reveals that the ocean's role as a sink for pollutants has limits and consequences. For decades, the ocean was treated as an infinite dumping ground, somewhere that waste could be sent and forgotten. Out of sight, out of mind. But the waste doesn't disappear. It accumulates, it persists, it enters food webs, and it affects ecosystems. The discovery of high concentrations of POPs in hadal organisms decades after these chemicals were banned shows that pollution can have long-lasting effects and can accumulate in unexpected places. Third, it raises questions about the health of deep-sea ecosystems and their ability to function properly under the stress of pollution. Deep-sea organisms have evolved over millions of years to thrive in extreme conditions of pressure, cold, and darkness. But they did not evolve to deal with synthetic chemicals, plastic particles, and heavy metals. We don't know what the long-term effects of this pollution will be. Will it affect reproduction rates? Will it alter food webs? Will it reduce the biodiversity and resilience of hadal ecosystems? These questions are just beginning to be investigated. Fourth, The pollution in the Mariana Trench connects surface activities to deep ocean consequences in ways that aren't immediately obvious. When someone throws a plastic bottle into a river in China, Indonesia, or the United States, they probably don't think about that bottle potentially ending up at the bottom of the ocean 7 miles deep. When industrial facilities release chemicals into the air or water, the global circulation of the atmosphere and ocean can transport those chemicals to the most remote parts of the planet. This interconnection means that pollution is everyone's problem and that solutions require global cooperation. What can be done about pollution in the Mariana Trench and the deep ocean more broadly? The challenges are immense. Unlike cleaning up pollution on land or even in shallow coastal waters, it's not feasible to send crews to the bottom of the Mariana Trench to collect plastic debris or to remediate contaminated sediments. The depth, pressure, and remoteness make such efforts impossible with current technology. Even if it were technically possible, the cost would be astronomical. The most practical approach is prevention, stopping pollutants from entering the ocean in the first place. This means improving waste management systems globally, particularly in countries where infrastructure is inadequate and where large amounts of plastic waste enter the ocean through rivers and coastal areas. It means transitioning away from single-use plastics and toward materials that are biodegradable or that can be effectively recycled. It means regulations to prevent industrial discharge of toxic chemicals and to clean up contaminated sites before pollutants can spread. It means international agreements to phase out the production and use of harmful chemicals like POPs. It means better management of fishing gear to prevent its loss at sea. It means education and cultural change to reduce consumption and waste generation. Some of these efforts are already underway. The Stockholm Convention on Persistent Organic Pollutants, which entered into force in 2004, is an international treaty designed to eliminate or restrict the production and use of POPs. Many countries have implemented bans on single-use plastic items like bags, straws, and styrofoam containers. There are initiatives to develop new materials that can replace conventional plastics, including bio-based and biodegradable alternatives. There are cleanup efforts targeting plastic accumulations like the Great Pacific Garbage Patch, though these are controversial and their effectiveness is debated. However, the scale of the problem is so large that even aggressive action will take decades to show results. Plastic already in the ocean will continue to break down and be transported to the deep sea for years to come. POPs already in the environment will persist for decades or even centuries before they fully degrade. The pollution that has already reached the Mariana Trench will likely remain there indefinitely. The sediments at the bottom of the trench accumulate slowly, and once pollutants are buried in those sediments, they essentially become a permanent part of the geological record, a marker of the Anthropocene epoch, when human activities became a dominant force shaping the planet. Scientists are also working on better monitoring of deep ocean pollution. By regularly sampling water, sediments, and organisms from the Mariana Trench and other deep-sea environments, researchers can track how pollution levels change over time. This monitoring can help assess whether efforts to reduce pollution are working and can provide early warning of new contaminants or emerging problems. Genetic studies of deep-sea microbes are also revealing that some bacteria have evolved the ability to degrade certain plastics and other synthetic compounds, raising the possibility that natural processes may eventually help break down some pollutants, though this is likely to be a very slow process. The story of pollution in the Mariana Trench is ultimately a story about the consequences of human actions and the interconnectedness of Earth's systems. It's easy to think of our individual actions as insignificant, to believe that one plastic bottle or one car trip or one chemical product doesn't matter in the grand scheme of things. But when billions of people make similar choices, the cumulative effect is enormous. The plastic bag at the bottom of Challenger Deep didn't get there by itself. It's there because of countless decisions made by countless people. The decision to manufacture single-use plastic products, the decision to purchase and use them, the decision to dispose of them improperly, and the failure of systems and policies to prevent plastic from entering the environment. The good news, if there is any in this sobering story, is that humans also have the capacity to change course. We have the technology and knowledge to reduce pollution. We have the ability to design products and systems that minimize environmental impact. We have the potential to develop a more sustainable relationship with the ocean and with the planet as a whole. The pollution in the Mariana Trench should serve as a wake-up call, a vivid reminder that there are no frontiers left where we can simply discard our waste and forget about it. Every part of the planet is connected, and what we do in one place affects everywhere else, even the most remote depths of the ocean. If we want future generations to inherit an ocean that is healthy and full of life, we need to act now to reduce pollution and to protect these extraordinary environments before the damage becomes irreversible. The exploration of the Mariana Trench represents one of the most demanding engineering challenges humanity has ever attempted to solve. Creating technology that can function at depths where the pressure exceeds 16,000 pounds per square inch, where the temperature hovers just above freezing, and where complete darkness prevails requires pushing the boundaries of materials, science, engineering design, and technological innovation. The history of deep-sea exploration is, in many ways, a history of technological advancement, with each generation of equipment enabling discoveries that were impossible for the previous generation. Let's explore the remarkable technologies that make it possible for humans and machines to venture into the deepest parts of the ocean and return safely with data and samples that expand our understanding of Earth. At the heart of any deep diving system is the pressure hull or pressure sphere. This is the component that must withstand the crushing force of the ocean at depth, while maintaining a safe, breathable environment for humans or protecting sensitive electronic equipment. The physics of pressure resistance dictate many aspects of deep-sea technology. Pressure increases linearly with depth, approximately 1 atmosphere, or 14.7 pounds per square inch, for every 33 feet of descent. At the bottom of Challenger Deep, the pressure is over 1,000 atmospheres. This creates compressive forces that would instantly crush any structure not specifically designed to resist them. The ideal shape for resisting external pressure is a sphere. A perfect sphere has no corners, edges, or flat surfaces where stress can concentrate. The pressure applied to a sphere is distributed evenly across the entire surface, and the compressive forces are channeled through the material toward the center. This is why pressure spheres for deep diving submersibles are manufactured to be as perfectly spherical as possible, with tolerances measured in fractions of a millimeter. Any deviation from perfect sphericity creates weak points where failure could initiate. The material used for pressure spheres must have extraordinary properties. It needs to be strong enough to resist the compressive forces without buckling or collapsing. It needs to be tough enough not to crack or shatter under stress. It needs to be resistant to corrosion from seawater, which is highly corrosive, especially at depth where the high pressure drives chemical reactions more aggressively. And ideally, it should be light enough that the overall vehicle can achieve neutral buoyancy or can be lifted by reasonable support equipment. Several materials have been used successfully for pressure spheres. Steel was used for the Trieste's pressure sphere in 1960. The sphere was made of forged steel approximately 5 inches thick and had an internal diameter of just over 6 feet. Steel is strong, well understood by engineers, and relatively easy to manufacture into complex shapes. However, steel is also heavy. The Trieste's pressure sphere weighed several tons, which meant the overall vehicle needed to be very large to provide enough buoyancy to support that weight. Despite its weight, steel performed well, and the Trieste sphere successfully protected Picard and Walsh during their historic dive. Titanium has become the material of choice for modern deep diving submersibles. Titanium alloys offer an excellent combination of strength, toughness, and corrosion resistance while being significantly lighter than steel. Titanium's strength-to-weight ratio is superior to steel, meaning a titanium sphere can be thinner than a steel sphere for the same pressure rating, reducing weight. The limiting factor, used by Victor Vescovo for his 5 Deeps expedition, has a pressure sphere made from titanium alloy that is approximately 3.5 inches thick. This sphere can accommodate 2 people and has been certified for unlimited dives to full ocean depth, meaning any point in the world's oceans, with a significant safety factor, The manufacturing of titanium pressure spheres is a complex process. The sphere for the limiting factor was forged in multiple pieces that were then welded together. The welding must be perfect, with no flaws, cracks, or inclusions that could serve as failure initiation points. After welding, the sphere undergoes extensive testing, including X-ray inspection, ultrasonic testing, and pressure testing. It's placed in a pressure chamber and subjected to pressures exceeding what it will experience at full ocean depth to ensure it can handle the stress. Only after passing all these tests is the sphere certified for use. Another material that has been considered for pressure hulls is ceramic composites. Ceramics can be extremely strong in compression, and some types are relatively light. However, ceramics are brittle and can shatter catastrophically if they crack. There have been experimental submersibles with ceramic pressure hulls for intermediate depths, but so far, no ceramic hull has been certified for full ocean depth. Research continues in this area, as an even lighter pressure hull material could enable smaller, more maneuverable submersibles. Acrylic and other transparent materials are used for viewports, allowing occupants to see out of the pressure sphere. Viewports are challenging because they must be transparent, yet strong enough to resist the pressure. The solution is to make viewports in the shape of a truncated cone or frustum, with the narrow end facing inward and the wide end facing outward. This shape allows the pressure of the ocean to actually push the viewport more tightly into its seat, creating a self-sealing effect. The viewport material is typically very thick, sometimes over 8 inches for full ocean depth applications. Despite this thickness, the viewports are relatively small, typically only a few inches in diameter for the clear aperture, limiting the field of view. Beyond the pressure sphere, deep diving submersibles need many other systems. Buoyancy is one of the most critical considerations. To descend, a submersible must be negatively buoyant, meaning it's heavier than the water it displaces. To ascend, it must be positively buoyant, lighter than the water it displaces. The Trieste used a simple but effective system. It had large tanks filled with gasoline, which is lighter than water and doesn't compress significantly under pressure. To descend, the Trieste carried iron pellet ballast. To ascend, it released the ballast, and the gasoline floats provided lift. Modern submersibles use variations on this concept. Syntactic foam is commonly used to provide buoyancy. Syntactic foam is a composite material made of hollow glass or ceramic microspheres embedded in a polymer matrix. The microspheres are individually strong enough to resist the pressure without collapsing, and the spaces inside them contain air or vacuum, providing buoyancy. Syntactic foam can be manufactured in large blocks that are attached to the outside of the submersible frame. The limiting factor uses large blocks of syntactic foam to achieve the buoyancy needed to lift the heavy titanium sphere, life support systems, batteries, and other equipment. Variable ballast systems allow the pilot to fine-tune the submersible's buoyancy. These typically consist of tanks that can be filled with water or emptied using compressed air or by pumping. By adjusting how much water is in the ballast tanks, the pilot can make the submersible neutrally buoyant, allowing it to hover at a specific depth or slightly positively or negatively buoyant to ascend or descend slowly. For safety, deep diving submersibles have expendable ballast, usually steel weights, that can be dropped in an emergency to ensure the vehicle will ascend even if all power is lost. These weights are held by mechanisms that fail safe to release, so if power is lost or if an automatic system detects a problem, the weights are automatically dropped. Propulsion and maneuvering systems are necessary for modern submersibles to move horizontally and to maintain position. Early deep diving vehicles like the Trieste had minimal propulsion and could only descend and ascend. Modern submersibles have multiple thrusters, essentially small propellers driven by electric motors that allow them to move forward, backward, sideways, and to rotate. The limiting factor has a total of 4 thrusters that give it 6 degrees of freedom in movement. These thrusters must be designed to work under extreme pressure. The motors are typically sealed in oil-filled chambers. Oil is incompressible and can be pressurized to match the external water pressure, protecting the motor internals while still allowing the motor shaft to turn and drive the propeller. Power systems are critical. Deep diving submersibles are battery-powered because internal combustion engines require air, which can't be brought in unlimited quantities, and because fuel tanks would need to withstand the pressure. Lithium-ion batteries, similar to those used in electric vehicles, are commonly used in modern submersibles because of their high energy density. However, these batteries must be housed in pressure-resistant containers. The limiting factor's batteries are housed in pressure-compensated containers filled with oil, similar to the thrusters. The oil allows the electronics and battery cells to function normally while being protected from the pressure. Life support systems maintain a breathable atmosphere inside the pressure sphere. Humans consume oxygen and produce carbon dioxide, so life support must provide fresh oxygen and remove carbon dioxide. Oxygen is typically stored in high-pressure tanks and released as needed to maintain the proper concentration in the sphere's atmosphere. Carbon dioxide is removed using chemical scrubbers, typically lithium hydroxide canisters, that absorb carbon dioxide through a chemical reaction. These are the same types of scrubbers used in spacecraft and in rebreathers used by deep-sea divers. Temperature control is another consideration. While the ocean at depth is cold, typically just above freezing, the interior of the pressure sphere can actually become warm during a dive due to the occupant's body heat and the heat generated by electronics. Some submersibles have heating systems for comfort, while others rely on passive heat management. The pressure sphere itself acts as a giant heat exchanger, with its large surface area in contact with the cold water. In some cases, active cooling might even be necessary if the interior becomes too warm. Communication with the surface is challenging because radio waves don't propagate well through water. Instead, deep-diving submersibles use acoustic communication, essentially underwater modems that encode data as sound waves. These acoustic systems can transmit text messages, sensor data, and telemetry to the surface support ship. However, the data rates are very slow compared to radio communication, typically just a few kilobits per second, and the range is limited by the acoustic environment. Sound travels well through water, but it can be scattered by temperature layers, bubbles, and marine life, creating interference and limiting reliable communication range to a few miles. Navigation underwater is also difficult because GPS signals don't penetrate water. Submersibles use several methods to determine their position. Inertial navigation systems use accelerometers and gyroscopes to track the vehicle's movements from a known starting position. By integrating acceleration over time, the system can calculate velocity and position. However, inertial systems accumulate errors over time. To correct these errors, submersibles also use acoustic positioning systems. The surface ship or deployed transponders on the seafloor emit acoustic pulses, and by measuring the time it takes for these pulses to reach the submersible and return, the system can triangulate the vehicle's position. Modern systems can achieve position accuracy of a few meters, even at full ocean depth. Sonar systems are essential for mapping the seafloor and detecting obstacles. Side-scan sonar can create images of the seafloor by sending out sound waves and measuring the reflections. Multi-beam sonar uses an array of transducers to create detailed three-dimensional maps. The limiting factor uses advanced multi-beam sonar that can map a swath of seafloor hundreds of meters wide as the submersible moves across the bottom. This data can be used to create detailed bathymetric maps showing the topography of the trench floor. Lighting systems for deep-diving vehicles must be powerful yet energy efficient. Modern LED technology has revolutionized underwater lighting. LEDs produce far more light per watt than the incandescent and halogen lights used in older submersibles, and they're more compact and reliable. The limiting factor and similar vehicles have arrays of LED lights that can illuminate the seafloor for filming and observation. However, even powerful lights only illuminate a limited area in the deep ocean. Seawater absorbs and scatters light, so visibility is typically limited to a few tens of meters at best, even with bright lights. Cameras are crucial for documenting deep-sea expeditions. Modern deep-diving submersibles carry multiple cameras capable of recording high-definition or even 4K video. These cameras must be housed in pressure-resistant housings. typically cylindrical chambers with thick acrylic windows for the lens. The housings may be pressure compensated, filled with oil to match the external pressure, or they may be designed to maintain 1 atmosphere of pressure internally, requiring thick walls. The James Cameron's Deep-Sea Challenger was equipped with multiple 3D cameras, specifically designed for filming in the deep ocean, resulting in stunning footage that was used in documentaries and IMAX films. Manipulator arms allow submersibles to interact with the environment, collecting samples, placing instruments, or moving objects. These robotic arms have multiple joints and may have grippers or specialized tools at the end. The arms must be designed to work under extreme pressure with sealed joints and pressure-compensated actuators. Operating a manipulator arm at depth requires skill, as the pilot must compensate for water resistance and the limited field of view through the viewports or cameras. The limiting factor has a manipulator arm that has been used to collect rock samples, biological specimens, and debris from the ocean floor. Sampling systems include various devices for collecting water, sediment, and organisms. Water samplers, called Niskin bottles, can be triggered at specific depths to capture a sealed sample of water that maintains its pressure and temperature until it's brought to the surface. Sediment corers can be pushed into the soft sediment to extract a cylindrical core sample that preserves the layering of the sediment. Biological sampling tools include nets, scoops, and suction devices that can capture organisms without damaging them too much. Now let's turn to remotely operated vehicles, or ROVs, which are uncrewed submersibles controlled from a ship on the surface through a tethering cable. ROVs have some advantages over crewed submersibles. They don't need to accommodate humans, so they can be smaller and don't need life support systems. They can remain at depth for extended periods, limited only by the endurance of their support ship rather than by the life support capacity for human occupants. And they don't put human lives at risk, making them suitable for very hazardous environments or experimental operations. The tether connecting an ROV to the surface ship carries power and communication signals. This allows the ROV to have effectively unlimited power from the ship's generators, rather than relying on batteries. It also allows for real-time, high-bandwidth communication, meaning the operators on the ship can see video feeds from the ROV's cameras with minimal delay and can control the vehicle precisely. However, the tether also creates limitations. It can be damaged by sharp rocks or debris. It creates drag that the ROV must overcome, and it limits the range of the ROV to the length of the tether, typically a few hundred meters to a few kilometers. For full ocean depth, the tether becomes a significant engineering challenge. A tether long enough to reach the bottom of the Mariana Trench, over 36,000 feet or nearly 7 miles, must be strong enough to support its own weight without breaking. It must be neutrally buoyant or slightly positively buoyant to reduce the load on the vehicle, and it must contain multiple conductors for power and data while being as thin as possible to minimize drag. Specialized tethers have been developed using high-strength synthetic fibers like Kevlar or Spectra for strength combined with copper wires, or fiber optics for power and communication, all enclosed in a protective sheath. Several ROVs have been built for Hadal depths. The Japanese ROV Kaiko reached the bottom of Challenger Deep in 1995 and conducted survey work and sample collection. It was a remarkable achievement, though sadly, Kaiko was lost at sea in 2003 when its cable broke during a dive. More recently, China has developed the Haidu-1 ROV system, which has explored the Mariana Trench at depths exceeding 33,000 feet. These vehicles have demonstrated that ROVs are viable for Hadal exploration and that they can perform tasks like sample collection and manipulation at extreme depth. However, the tether remains a limiting factor. This has led to interest in hybrid systems called hybrid remotely operated vehicles, or HROVs, or in fully autonomous underwater vehicles, or AUVs. AUVs have no tether. They're essentially underwater robots that navigate and operate independently using pre-programmed missions or artificial intelligence. AUVs carry their own power in onboard batteries, which limits their endurance, and they must be able to navigate and make decisions without real-time human input. For Hadal depths, AUVs face all the same pressure-related challenges as crewed submersibles and ROVs, but with the added complexity of needing sophisticated autonomy. An AUV must be able to map the environment using sonar, avoid obstacles, collect data or samples according to its mission profile, and return to a recovery point, all without human intervention. If something goes wrong at the bottom of the Mariana Trench, there's no tether to provide a lifeline and no human pilot to make real-time decisions. Despite these challenges, AUV technology is advancing rapidly. There are AUVs designed for deep water, though most are rated for abyssal depths of around 20,000 feet, rather than full Hadal depths. Developing AUVs for full ocean depth is an active area of research. Such vehicles would enable large-scale, systematic exploration and mapping of trenches, covering far more area than is possible with the limited time available in crewed submersibles or tethered ROVs. Another category of deep-sea technology is the autonomous lander. Landers are free-falling vehicles that descend to the seafloor under their own weight, remain there for a period of time conducting observations or experiments, and then return to the surface by dropping ballast. Landers are relatively simple and cost-effective compared to crewed submersibles or sophisticated ROVs. They typically consist of a frame made of aluminum or titanium, with syntactic foam for buoyancy, scientific instruments such as cameras, bait to attract organisms, sampling devices, and an expendable ballast weight held by an acoustic release mechanism. To deploy a lander, it's pushed off the side of a ship with the ballast attached. It falls freely through the water column, a journey that can take several hours for very deep deployments. Once on the bottom, the lander operates autonomously according to its programming. Cameras might take time-lapse photographs or record video of organisms attracted to bait. Sensors might measure temperature, salinity, or chemical parameters after a predetermined time or when commanded by an acoustic signal from the ship. The lander releases its ballast, and the buoyancy from the syntactic foam causes it to ascend to the surface, where it's recovered by the ship. Landers have been extensively used in Hadal research. Multiple research groups have deployed landers to the Mariana Trench and other deep trenches, resulting in thousands of hours of footage and numerous samples. Landers are particularly good for studying undisturbed behavior of deep-sea organisms, because after the initial disturbance of the landing, the lander sits quietly on the bottom and organisms approach it naturally, especially if it has bait. This has provided valuable insights into Hadal ecology and behavior that wouldn't be possible with crewed submersibles or ROVs, which create disturbance with their lights and movements. The materials science behind all of these deep-sea technologies is fascinating. Engineers must carefully select materials that can withstand not just the pressure, but also the corrosive effects of seawater, the low temperatures, and the mechanical stresses of deployment and recovery. Aluminum alloys are commonly used for frames and structural components because of their high strength-to-weight ratio and good corrosion resistance, especially when anodized. Titanium is used where higher strength or better corrosion resistance is needed. Stainless steel is used for certain components, though it's heavier than aluminum or titanium. Seals and O-rings are critical components. They must prevent water from entering pressure housings, while allowing moving parts like propeller shafts to rotate. At extreme depth, the water pressure can extrude O-rings, pushing them through any gaps. This is prevented by using special seal designs with backup rings and by using materials that maintain their flexibility and sealing properties under high pressure. Compounds like Viton fluoroelastomer are commonly used because they resist compression and maintain their elastic properties even when cold and under high pressure. Electronics for deep-sea vehicles must be specially designed or protected. Standard electronics can be damaged by pressure if water enters their housings. The solution is either to house electronics in pressure-resistant containers that maintain 1 atmosphere internally, or to pot electronics in epoxy, encasing them in a solid block of material that can't be compressed. Pressure-tolerant electronics that are potted or otherwise protected can function even when exposed to full ocean pressure, allowing for simpler designs without heavy pressure housings. Sensor technology for the deep ocean includes a wide variety of instruments. CTD sensors measure conductivity, temperature, and depth, providing information about water properties. Oxygen sensors measure dissolved oxygen concentration. Chemical sensors can detect specific compounds like methane, hydrogen sulfide, or carbon dioxide. Biological sensors might include acoustic devices to detect fish or other organisms, or environmental DNA samplers that filter water to collect genetic material from organisms in the area. One area of ongoing technological development is improving power sources. Current batteries limit the endurance of untethered vehicles. Researchers are investigating higher energy density batteries, fuel cells that could generate power from chemical reactions, and even nuclear power sources, similar to those used in some spacecraft and military submarines, though the latter are controversial and face regulatory and safety challenges. Longer endurance would enable vehicles to spend more time at depth, cover greater distances, and conduct more extensive research without needing to return to the surface. Another frontier is in improving communication bandwidth underwater. Acoustic communication is inherently limited in data rate. Researchers are investigating optical communication using blue-green lasers, which can achieve higher data rates over short distances in clear water. Such systems might allow real-time streaming of high-definition video from deep-sea vehicles, something that's not possible with current acoustic systems. However, optical communication requires a clear line of sight and is sensitive to water clarity, making it challenging in some environments. Artificial intelligence and machine learning are beginning to play a role in deep-sea exploration. AI can help autonomous vehicles navigate complex terrain, identify interesting features or organisms to investigate, and optimize sampling strategies. Machine learning algorithms can analyze vast amounts of sonar data to create detailed maps or to identify geological features. Computer vision systems can identify and count organisms in video footage, a task that would be impossibly time-consuming for humans to do manually, given the thousands of hours of footage collected by landers and ROVs. Virtual reality and telepresence technologies are enhancing how scientists interact with deep-sea data. Instead of watching video on a flat screen, researchers can use VR headsets to immerse themselves in three-dimensional reconstructions of the seafloor created from sonar and photographic data. This can provide new insights and make it easier to understand the spatial relationships between features. Telepresence systems allow scientists on shore to participate in real time in research cruises at sea, watching live video feeds from ROVs and communicating with the shipboard team, reducing the need for expensive and time-consuming research voyages. Safety systems are paramount in deep-sea technology. Crewed submersibles have multiple redundant systems for critical functions. The limiting factor, for example, has multiple independent methods for dropping ballast to ensure ascent. It has backup life support systems. It has multiple communication systems. It has tracking beacons and emergency locators, so it can be found even if it surfaces far from the support ship. Before each dive, extensive checklists are followed to verify that all systems are functioning properly. The submersible undergoes regular maintenance and inspection, with critical components like the pressure sphere being periodically tested to ensure they remain within specifications. Certification and testing protocols for deep diving vehicles are rigorous. Independent classification societies like DNVGL or the American Bureau of Shipping review the design and construction of submersibles and certify them for specific depth ratings. This process involves reviewing calculations, inspecting materials and welds, witnessing pressure tests, and verifying safety systems. Only after passing all requirements is a certificate issued, allowing the submersible to operate at its rated depth. This certification must be periodically renewed, with inspections and testing to ensure the vehicle remains in safe condition. The cost of deep-sea technology is substantial. Building a submersible like the limiting factor costs tens of millions of dollars. Operating it requires a support ship, which can cost tens of thousands of dollars per day, a crew of engineers and technicians, spare parts, and extensive logistical planning. Even relatively simple landers can cost hundreds of thousands of dollars when you include the instruments, cameras, and support equipment. This high cost is one reason why deep-sea exploration has been limited and why we've explored such a small fraction of the ocean floor. However, costs are beginning to decrease as technology matures and as more players enter the field. Commercial companies are developing submersibles for tourism, scientific research, and even resource extraction, driving innovation and competition. Advances in manufacturing techniques like additive manufacturing or 3D printing may reduce costs for certain components. Improvements in batteries, electronics, and materials will enable smaller, lighter vehicles that are cheaper to build and operate. Looking to the future, there are ambitious proposals for even more advanced deep-sea technologies. Some researchers envision swarms of small, inexpensive AUVs that could be deployed in large numbers to simultaneously map and study large areas of the ocean floor, communicating with each other and coordinating their activities. Others propose underwater habitats at moderate depths that could serve as bases for deeper exploration, allowing researchers to live underwater for extended periods. There are even concepts for biomimetic vehicles that mimic the swimming of fish or other marine animals, potentially achieving greater efficiency and maneuverability than current designs. The technologies that enable exploration of the Mariana Trench represent some of humanity's most impressive engineering achievements. They push the boundaries of what's possible and demonstrate that with sufficient ingenuity, creativity, and resources, humans can explore even the most extreme environments on our planet. Each generation of technology builds on the lessons learned from previous generations, gradually expanding our capabilities and our understanding. From the pioneering Trieste with its simple steel sphere and gasoline floats to modern marvels like the limiting factor with its titanium sphere, sophisticated sensors, and AI-assisted navigation, the evolution of deep-sea technology has been remarkable. These technologies don't just enable exploration for its own sake. They provide the tools necessary to study deep-sea ecosystems, to understand geological processes occurring in trenches, to discover new species and new biochemical pathways, and to monitor the health of the ocean in the face of human impacts like pollution and climate change. They allow us to venture into a realm that is, in many ways, more alien and less accessible than outer space, and to bring back knowledge that enriches our understanding of our home planet. As technology continues to advance, we can look forward to even more extensive exploration of the Mariana Trench and Earth's other deep ocean environments, uncovering secrets that have remained hidden for millions of years, and perhaps finding answers to questions we haven't even thought to ask yet. The Mariana Trench stands as a profound reminder of how much remains unknown about our own planet. We live in an age where we've mapped the surface of Mars in higher resolution than we've mapped our own ocean floor, where we've detected thousands of exoplanets orbiting distant stars, where we've sent probes to the outer reaches of our solar system, and yet the deepest parts of our own ocean remain largely unexplored. This paradox tells us something important about the human condition, about our tendency to look outward while overlooking what lies beneath. But more than that, the mysteries of the Mariana Trench offer lessons that extend far beyond the specific creatures and conditions found there. They provide insights into the nature of life itself, the resilience of living systems, the interconnectedness of our planet, and even the possibilities for life beyond Earth. Let's begin with what the trench teaches us about the adaptability and tenacity of life. Before humans descended to Challenger Deep, before we had evidence that life could survive at such extreme depths, many scientists believed there must be a depth limit beyond which life could not exist. The reasoning seemed sound. The pressure becomes so great, the conditions so harsh, that biochemical processes would break down. Proteins would denature, cell membranes would lose function, and organisms simply could not maintain the complex chemistry that defines life. The discovery of thriving ecosystems at the bottom of the Mariana Trench shattered this assumption completely. Life exists at the bottom of the trench not in spite of the extreme conditions, but in many ways because of its adaptations to those conditions. The organisms there have evolved biochemical solutions to the challenge of extreme pressure, including specialized molecules like TMAO that stabilize proteins and modified cell membranes that remain fluid under compression. They've developed life strategies suited to a world of perpetual darkness and scarce food, including slow metabolisms, efficient scavenging behaviors, and the ability to detect rare food opportunities from great distances. They've shown that life is not a fragile phenomenon confined to a narrow range of conditions, but rather an extraordinarily adaptable and resilient process that can find a way to persist in almost any environment where liquid water exists and where there's an energy source to power metabolism. This realization has profound implications for how we think about life on Earth and beyond. If life can thrive at the bottom of the Mariana Trench, under pressures that would crush most organisms, in temperatures just above freezing, in complete darkness, then the definition of habitable environments must be expanded. We can no longer assume that life requires sunny, warm, oxygen-rich conditions. Life can exist in the absence of sunlight, deriving energy from chemical reactions rather than photosynthesis. It can exist without oxygen, using other molecules as electron acceptors in metabolism. It can exist under pressures and in temperatures that we once considered incompatible with biology. This expanded definition of habitability has direct implications for astrobiology, the search for life beyond Earth. When we look at other worlds in our solar system and ask where life might exist, the lessons from the Mariana Trench suggest we should look not just at the surfaces of planets, but at their subsurfaces, at environments that might seem inhospitable, but that could harbor life adapted to those conditions. Europa, one of Jupiter's largest moons, is covered in ice, but is believed to have a global ocean of liquid water beneath its frozen surface. This ocean is kept liquid by tidal heating, the gravitational flexing caused by Jupiter's immense gravity. The ocean beneath Europa's ice could be several miles deep, and it exists in complete darkness, under significant pressure, at temperatures near freezing. Sound familiar? The similarities between the deep ocean of Europa and the Mariana Trench are striking. Both are cold, dark, high-pressure environments with liquid water. If life can exist at the bottom of the Mariana Trench, then it's not unreasonable to speculate that life could exist in Europa's subsurface ocean. There would need to be an energy source to power metabolism. On Earth, life in the deep ocean ultimately derives most of its energy from the sun through the sinking of organic matter from the surface, though chemosynthetic ecosystems near hydrothermal vents can derive energy from geological processes. On Europa, there might be hydrothermal vents on the ocean floor where the tidal heating creates volcanic activity, providing chemical energy that life could exploit. There might be other chemical gradients or energy sources we haven't even imagined. The point is that the existence of life in Earth's deepest ocean demonstrates that such environments are not inherently sterile. The same reasoning applies to other worlds. Enceladus, a small moon of Saturn, also appears to have a subsurface ocean beneath its icy crust. Geysers of water vapor and ice particles erupting from cracks in Enceladus's south polar region have been detected by spacecraft, and analysis of these plumes has revealed the presence of organic molecules, salts, and other compounds consistent with a habitable ocean environment. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane on its surface rather than water, but it might also have a subsurface water ocean. Even Mars, which appears barren and frozen on the surface, might have liquid water in subsurface aquifers or in temporary seasonal flows. Each of these environments, if they exist, could potentially harbor life, and the organisms of the Mariana Trench show us what adaptations might make life possible in such extreme conditions. Beyond the solar system, the discovery of thousands of exoplanets orbiting other stars has revealed that planetary systems are common in our galaxy. Some of these planets are located in their star's habitable zone, the region where temperatures could allow liquid water on the surface. But the lessons from the Mariana Trench suggest we shouldn't focus exclusively on surface conditions. Exoplanets with thick atmospheres, global oceans, or subsurface water layers could potentially harbor life, even if their surface conditions seem inhospitable. The concept of habitability is much broader than we once thought, and the Mariana Trench has been instrumental in expanding that concept. The trench also teaches us about the limits of life and the boundaries between what is possible and what is not. While life has been found at the bottom of Challenger Deep, there does appear to be a depth limit for certain types of organisms. Fish have not been observed below approximately 27,000 feet, close to a theoretical limit imposed by the effects of pressure on protein function, even with maximum concentrations of protective molecules like TMAO. Below this depth, only invertebrates and microorganisms are found. This suggests that there are fundamental constraints on biology imposed by the laws of physics and chemistry. No amount of evolutionary adaptation can overcome certain physical limitations. Understanding these limits is important for astrobiology. It tells us that while life might be possible in a wide range of environments, there are boundaries beyond which even the most adaptable organisms cannot survive. On worlds with even more extreme conditions than Earth, such as planets with crushing atmospheric pressures or temperatures hot enough to break down complex molecules, life as we know it probably cannot exist. However, the caveat, as we know it, is important. All life on Earth shares a common biochemistry based on carbon, water, and certain types of molecules like proteins and nucleic acids. It's conceivable that life could evolve using different chemistry on worlds with radically different conditions. Silicon-based life, or life using liquid methane as a solvent instead of water, has been speculated about by scientists and science fiction writers. We have no examples of such life, and we don't know if it's possible. But the diversity of life in extreme environments on Earth, including the Mariana Trench, shows us that life is more creative and adaptable than we often assume. The discovery of pollution in the Mariana Trench teaches us a different but equally important lesson: the interconnectedness of Earth's systems and the global reach of human impact. We tend to think of our actions as having local consequences. We throw away a plastic bottle, and it ends up in a landfill or perhaps in a nearby river. We don't think about that bottle potentially making its way to the ocean, breaking down into microplastics, becoming incorporated into marine food webs, and eventually reaching the bottom of the deepest trench on Earth. But that's exactly what happens. The plastic bag observed at the bottom of Challenger Deep didn't teleport there. It traveled over months or years through a complex series of processes involving ocean currents, sinking, biological interactions, and perhaps other mechanisms we don't fully understand. Its presence there is a direct consequence of human behavior thousands of miles away and perhaps years in the past. This interconnectedness means that there is no away where we can send our waste and forget about it. Every action we take, every piece of trash we generate, every chemical we release into the environment has consequences that ripple outward through Earth's systems. Some of those consequences are immediate and obvious. Others take decades to manifest and affect places we've never visited and may never see. The pollution in the Mariana Trench is a warning that our planet is finite, that its systems are interconnected, and that we must take responsibility for our impacts if we want to preserve the health of the biosphere that sustains us. This lesson also applies to other worlds we might explore or colonize in the future. Mars missions are currently being planned with the goal of eventually establishing human settlements on the Red Planet. As we extend our presence beyond Earth, we carry the risk of contaminating other worlds with Earth organisms or with pollution from our activities. The challenge of protecting pristine environments from human impact is not unique to Earth. If we discover life on Mars or Europa or elsewhere, we'll face ethical questions about how to study it without disturbing or contaminating it. The experience of seeing pollution, even in the Mariana Trench, one of Earth's most remote places, should inform how we approach exploration and potential settlement of other worlds. We have an opportunity to do better, to explore and utilize space in ways that minimize harm and preserve the integrity of extraterrestrial environments. The Mariana Trench also teaches us about the importance of exploration and the value of curiosity-driven research. The expeditions to Challenger Deep were expensive, technically challenging, and risky. Someone might reasonably ask, why bother? Why spend tens of millions of dollars to send people or robots to the bottom of the ocean when there are pressing problems to solve on the surface? The answer is that exploration yields knowledge, and knowledge has value that's difficult to quantify, but nonetheless real and important. The organisms discovered in the Mariana Trench have already led to insights in biochemistry, materials science, and evolutionary biology. The piezolites that protect deep-sea proteins from pressure damage are being studied for potential applications in stabilizing pharmaceuticals and industrial enzymes. The geology of subduction zones, studied partly through research in trenches, helps us understand earthquake mechanisms and improves our ability to predict and prepare for seismic hazards. But beyond practical applications, exploration satisfies a fundamental human need to understand our world and our place in it. The Mariana Trench is part of our planet, part of the system that sustains us, and understanding it is part of understanding ourselves. The sense of wonder and awe that comes from learning about life at the bottom of the ocean, from seeing footage of strange creatures living in eternal darkness under crushing pressure, from grasping the sheer scale and complexity of Earth's systems. This sense of wonder is valuable in itself. It reminds us that we live on an extraordinary planet, that nature is more remarkable than any fiction we could invent, and that there's always more to learn. The mysteries that remain in the Mariana Trench, the species yet to be discovered, the geological processes yet to be fully understood, the ecosystems yet to be mapped. These mysteries are an invitation to future generations of scientists and explorers. They represent opportunities for discovery, for advancement of knowledge, for solving puzzles that have remained hidden for millions of years. Every mystery solved opens up new questions. Every answer leads to deeper inquiry. This is the nature of science and exploration, an endless journey into the unknown that continually expands the boundaries of human understanding. Philosophically, the Mariana Trench confronts us with the limits of human perception and the humility that should come from recognizing those limits. For the vast majority of human history, we had no idea that places like the Mariana Trench existed. We knew the ocean was deep, but we couldn't conceive of depths measured in miles, of pressures measured in thousands of atmospheres, of ecosystems that function in perpetual darkness. Our understanding of the world was shaped by what we could see and experience directly. As technology has expanded our ability to explore beyond those immediate sensory limits, we've discovered that the world is far stranger and more complex than we imagined. This should make us cautious about assuming we understand everything or that our current knowledge is complete. At any given moment in history, humans have tended to believe they've figured out most of the important things about the world. And at every point, subsequent discoveries have shown how much remained unknown. In the 19th century, scientists thought physics was nearly complete, with just a few minor details left to work out. Then came relativity and quantum mechanics, completely revolutionizing our understanding of reality. In biology, the discovery of DNA and the molecular basis of genetics transformed our understanding of life. The discovery of hydrothermal vent ecosystems in the 1970s overturned assumptions about where life could exist and how ecosystems could function. The Mariana Trench reminds us that we're still in the early stages of understanding our planet. We've explored less than 20% of the ocean floor. We've catalogued only a fraction of marine species. We're still discovering fundamental things about how Earth systems work. This should instill a sense of humility and openness to new discoveries that challenge our assumptions. It should make us suspicious of overly confident claims about what is or isn't possible, what can or cannot exist. The universe has a way of surprising us, and the best scientific stance is one of curiosity combined with skepticism, of proposing hypotheses while remaining open to evidence that contradicts them.